Organized by Vinayaka Missions Kirupananda Variyar Arts and Science College, a Constituent College of Vinayaka Missions Research Foundation, deemed to be University, Salem. The Core Facility Center for Photochemistry and Nanomaterials, the Research Institute of Natural Science, Gyeongsang National University, South Korea, and Chulalongkorn University, Thailand. I welcome all the eminent speakers and guests from all over the country, from different walks of life. They have come here to share their knowledge and vast experience. This is the third international conference in the history of our college. Previously, we had successfully conducted 2 international conferences in the digital platform. It's our pleasure to invite the guest of the day, the management, respected chief guests, guests of honors, our principal sir, and principals from various colleges, beloved faculty members and non-teaching staff, and last but not least, our enthusiastic participants who are present here in today's international conference. On behalf of the institution, I offer my regards to all the dignitaries on and off the dais. Once again, I welcome you all on this delightful occasion. Everyone can rise above their circumstance and achieve success if they are dedicated to and passionate about what they do. The words of Mother Teresa, a noble philanthropist and educationalist, established Tirumuruga Kirupananda Variyar Tavathiru Sundara Swamigal Medical, Educational and Charitable Trust in the year of 1981. With the heavenly blessings of Dr. A. Shanmugasundaram, Founder Chancellor of Vinayaka Mission Research Foundation, deemed to be University, with the benevolence of Mrs. Annapurani Shanmugasundaram, Madam, Founder Chancellor of Vinayaka Missions Research Foundation, deemed to be University, with the blessings of them, we begin this occasion. Education is the most powerful weapon which you can use to change the world. The pedestal of Vinayaka Missions Research Foundation, deemed to be University, Dr. A.S. Ganesan Sir, Chancellor, and Dattosri Dr. S. Saravanan, Pro-Chancellor Sir. With the blessings of them, we begin this delightful occasion.
Unity is strength. When there is teamwork and collaboration, wonderful things can be achieved. I request all the delegates to occupy their seats on the dais. One song can change a moment. One idea can change a world. One step can start a journey. But a prayer can change even the impossible. I kindly request all to stand for the prayer song. Thousands of candles can be lightened from a single candle. Happiness never decreases by being shared. This was said by Buddha. The lamp burns to remind who are present of peace and positive brightness. I request all the dignitaries to lighten the lamp. Thank you, dignitaries. Francis Bacon once said, "Reading maketh a full man, conference a ready man, and writing an exact man. A man with perfection in all actions. Every day walks extra miles to achieve greater dreams for the future of young minds. Firm in discipline, but at the same time gentle in heart." It is none other than our beloved vibrant principal, Dr. V. Anbaragan, sir. I request him to bear a welcome speech.
So very good morning to all of you, respected dignitaries and participants. With the heavenly blessings of our Honorable Founder Chancellor Dr. A. Shanmugasundaram, I wholeheartedly welcome you all for this Indo-South Korea-Thailand 3rd International Conference on Nanoscience and Nanotechnology for Energy, Environment and Biomedical Applications. It is simply called as INEEBA-2023. The sole purpose of the conference is empowering the scientific aptitude in the field of nanoscience and nanotechnology. In keeping with this view, to empower the future leaders of world science, I wholeheartedly welcome you all for this inaugural function of this INEEBA 2023. This event is jointly organized by our Vinayaka Missions Kirupananda Variyar Arts and Science College, a constituent college of Vinayaka Missions Research Foundation deemed to be university, in collaboration with Core Facility Center for Photochemistry and Nanomaterials, Gyeongsang National University, South Korea, Chulalongkorn University, Thailand. We have conducted 2 similar conferences through online platform. It was very successful with the international standard. We had more than 250 participants in each online sessions. In these conferences, we have published our conference proceedings with ISBN numbers. Also, we have collaborated with the journals for publishing as a special issue in the Journal of Applied Biochemistry and Biotechnology, as well as Materials Today proceeding in the last INEEBA 2022. So, I wholeheartedly welcome our mother, Madam Founder Chancellor, for this August gathering. It is my great privilege and pleasure to welcome our Honorable Vice President, Mr. N.V. Chandrasekhar, sir, for this inaugural function. Sir has been a constant source of encouragement and motivation throughout the planning and execution phases of the conference. His words of wisdom and belief in our vision have boosted our team's confidence and kept with us focused on our goals. I wholeheartedly welcome you, sir. I also welcome our director, Mr. N. Ramasamy, sir, who has accepted our invitation to come forward for grace this inaugural function. I wholeheartedly welcome you, sir. I also welcome our Vice Chancellor, Professor Dr. P.K. Sudhir sir, for accepting our invitation even in holidays for gracing this function. Sir, your presence today adds immense significance to the event. We are honored to have you with us. Your guidance and vision have been instrumental in steering our institution towards excellence. I wholeheartedly welcome you, sir. It's also my immense pleasure to welcome our registrar, beloved Professor Dr. A. Nagappan, sir, for this August gathering. He is the instrumental right from the beginning of our INEEBA 2023. He is also organizing secretary of this INEEBA 2023 conference. I also welcome Professor Dr. Elil Vendan, Dean of VMKV Medical College, who is supporting us by providing all sort of facilities for conducting this INEEBA 23 in a successful manner. I welcome you, sir. I also welcome today's guest of honor, Professor Dr. Myung Yang Choi, Professor of Chemistry and Director of Center for Core Facility Center for Photochemistry and Nanomaterials, Gyeongsang National University. I wholeheartedly welcome you, sir. In addition to that, I also welcome Dr. Tirthagiri and Xiang Park from Gyeongsang National University. And I also welcome a team of 4 members from Chulalongkorn University, Thailand, Professor Anangnet from Chulalongkorn University, Professor Mananya Sutuping, Professor Manasvi Sutuping, Professor Dr. Vanvisha. I also welcome our deans of faculty members and principals of various our constituent colleges and deputy dean of VMK Medical College. I wholeheartedly welcome everyone for this INEEBA 2023. I also welcome my organizing team, Dr. Jayakandan, Dr. Prakash, Dr. Ganesha Murthy, Dr. Saini Jai and Mr. Ramesh for their volunteer in organizing such a mega event right from the beginning. I also welcome my research supervisor, Professor R. Ranganathan sir. He has come from Bharathadasan University. I welcome you, sir. Last but not least, I extend warm welcome to all the participants who are most beneficiaries of today's program. All the participants from various institutions across the country and nation who have chosen to spend your precious holiday time for attending this conference. It's truly inspiring insight to see many dedicated individuals gathered here today, willing to invest their free time in the pursuit of knowledge and growth. I have no doubt that the experiences and insights you gain during this conference will be well worth and filled with inspiration, enlightenment, and renowned source of purpose. I also welcome everyone gathered here for this INEEBA 2023. Thank you very much.
Thank you, sir.
Honor. The purpose of life is not to be happy, to be useful, to be honorable, to be compassionate. To have it make some difference that you have lived and lived well. Now it's time to honor today's guest. உலக மக்களால் அதிக பேசப்படுகின்ற ஒரே மொழி தமிழ். அதில் உலக பொதுமறைய நூலாக விளங்கும் ஒரே நூல் திருவள்ளுவர் இயற்றிய திருக்குறள். வாழ்வியல் சார்ந்த அனைத்து செய்திகளையும் கருத்துக்களையும் உலகத்திற்கு கூறியுள்ள ஒரே நூல் திருக்குறள். வள்ளுவன் தன்னை உலகிற்கு தந்து வான்புகழ் கொண்ட தமிழ்நாடு என பாரதியாரும், வள்ளுவனை பெற்றதால் பெற்றதே புகழ் வையகம் என பாரதிதாசனும் புகழ்ந்து பாராட்டியிருக்கிறார். அத்தகைய சிறப்பு வாய்ந்த திருவள்ளுவரின் உருவச்சிலையை சிறப்பு விருந்தினர்களுக்கு நினைவு பரிசாக வழங்குவதில் பெருமிதம் கொள்கிறோம். I request our principal sir to honor Sri Chandru sir. Mr. B. Dasaprakasam sir, Head Department of English and Development Officer, to honor Sri N. Ramasamy sir. I invite Dr. M. Prakash, HOD of Computer Science, to honor Professor Dr. P.K. Sudhir sir. Once again, I welcome our Principal sir to honor today's Professor Dr. Myong Yong Choi. Once again, I invite Dr. M. Prakash sir to honor Registrar sir. May I invite Mr. V. Ramesh sir, HOD of Commerce Department, to honor Dr. Elil Vendan sir. I request Dr. R. Ganesamurthy, Head Department of Chemistry, to honor Dr. J. Tirthagiri sir. I request Dr. M. Jayagandhan, Head Department of Physics, to honor Julian Park. Once again, I request our Principal sir to honor Dr. S. Anandan sir. I request Dr. E. Shiny Joy to honor Agagnon.
I now request Dr. S. Priyadarshini ma'am, Assistant Professor, Department of English, to honor Dr. Manunya ma'am.
I request M. Suguna ma'am, Associate Professor, Department of Computer Science, Vinayaka Mission, Kirupananda, Variyar, Arts and Science College, to felicitate Professor Dr. Manasvi Sitipong.
I now request N. Kasturi, Professor and Head, Department of Mathematics, to felicitate Professor Dr. Vanvisa Limfirat.
Thank you, sir.
Good leaders build products. Great leaders build cultures. Good leaders deliver results. Great leaders develop people. Good leaders have vision. Great leaders have values. Good leaders are role models at work. Great leaders are role models in life. He is a man of simplicity, elegant, enthusiastic man of letters. May I request Vice President of Vinayaka Mission's Research Foundation, deemed to be University Salem, Shri N.V. Chandrasekhar sir, to deliver a presidential address.
A respected guest of honor, Professor Dr. Myong Choi, Director for Core Facility Center for Photochemistry and Nanomaterials from Gyeongsang National University, South Korea. Respected Director of Vinayaka Missions, Mr. N. Ramaswamy. Respected Vice Chancellor, Professor Dr. P.K. Sudhir. Respected Registrar, Professor Dr. A. Nagappan. Respected Dean of VMKV Medical College, Professor Dr. K. Erilvendan. Respected speakers from various countries for this international conference. Respected Deans and Principals of Constituent College of VMRF. Respected Principal of VMKV Arts and Science College, Professor Dr. V. Anbergen. Respected Head of the Departments, faculty members, staffs of VMKV Arts and Science College, dear students and esteemed participants, good morning to one and all. With the heavenly blessings of our founder chairman and with the benevolence of our Madam Founder Chairman, it gives me immense pleasure to be in the inaugural function of this prestigious Indo-South Korea-Thailand Third International Conference on Nanoscience and Nanotechnology for Energy, Environment and Biomedical Applications, INEEBA-2023, in joint collaboration of VMKV Arts and Science College, Salem, along with Core Facility Center for Photochemistry and Nanomaterials, Gyeongsang National University, South Korea, and Department of Chemical Engineering, Chulalongkorn University, Thailand. At the outset, I would like to congratulate the principal of VMKV Arts and Science College, Professor Dr. V. Anbergen, and the organizing committee for hosting this conference and making extra efforts to make this conference a grand success. Being able to organize these events with key speakers from all over the world in the growing technology of nanoscience and nanotechnology is a very remarkable work. It is the third series of the conference in the emerging field of nanoscience, nanotechnology, and biomedical applications. For the past 3 years, our VMKV Arts and Science College is collaborating with the Gyeongsang National University, South Korea, and Chulalongkorn University, Thailand, and have conducted 2 international conferences, INEEBA-2021 and INEEBA-2022, via the online mode. Participants from all around the world have participated in these conferences and submitted their presentations. The selected papers were published in highly reputed international journals. In this August movement, I would like to convey the best wishes from our Honorable Pro-Chancellor, Dr. S. Saravanan, and Honorable Chancellor, Dr. A.S. Ganesan, for the success of this international conference. The potential of nanotechnology is boundless, and our collective efforts in research, development, and application will continue to shape the new world. The next 2 days, we shall have the opportunity to explore cutting-edge research in nanoscience and nanotechnology through enlightening discussions and collaborations with the subject experts. This is a great opportunity for the students and participants to interact with the international speakers and get to know the latest technologies and their applications. I would again like to welcome our guest of honor, Professor Dr. Myong Choi from Gyeongsang National University, and all the international speakers from South Korea and Thailand and other countries for this international conference and their active participations and inspiration to the young minds to create better solutions. Thanks to all the sponsors and all the members who have worked tirelessly for the success of this international conference. My congratulations again to our principal, Professor Dr. V. Anbaragan, and all the team members for the elaborate arrangements for these 2-day events. I am sure the conference will be fruitful and exciting to all the participants, and we are all looking forward to the outstanding contributions to the society from this 3rd International Conference, INEEBA 2023. Thank you all.
Thank you, sir. We feel empowered and encouraged by your mesmerizing words. To provide direction and to have courage to go first and create a better tomorrow for one followers. He is a man of hard work with vision. 36 years of experience in teaching, research and administration in a single institution. He has published more than 100 research articles in highly reputed journals. He has raised from the post of Principal, Vinayaka Mission's Kirupananda Variyar Engineering College and Director IEE. Now, he is appointed as the Registrar of Vinayaka Mission's Research Foundation, deemed to be university. It's my privilege to welcome our respected Registrar, Sir, Professor Dr. A. Nagappan, despite his busy schedule. I kindly invite Sir to felicitate the gathering.
Respected chief guests of today's international conference and our beloved Vice President of VMRF DU, Shri N.V. Chandrasekhar sir. Guest of honor, Professor Dr. Myong Choi, the Director for Core Facility Center for Photomaterials and Nanomaterials, Gyeongsang National University, South Korea. Our beloved Director, Mr. N. Ramasamy sir. Our beloved Vice Chancellor, Professor Dr. P.K. Sudhir, the Dean of this esteemed medical college, and my dear friend Dr. Elil Vendan, the invitees from Gyeongsang University and Chulalongkorn University, Thailand, invited delegates from national institutes of importance, my dear colleagues, head of the institutions, and invited participants. I take this privilege to felicitate this distinguished gathering of Indo-South Korea-Thailand 3rd International Conference on Nanoscience and Nanotechnology for Energy, Environment and Biomedical Applications as organizing secretary of the conference. This conference have received around 420 articles, participants from different countries as well as from different states of the nation. I am really astonished about the outcomes of the past two events through online. Speakers from 8 different countries gave their insights and findings in the field of nanoscience and nanotechnology for various applications. I am happy to inform you that Vinayaka Mission Research Foundation deemed university is in line with both universities of Thailand and South Korea for collaborative research, and we are working together in the field of nanomaterials, photochemistry, and on biomedical applications. I have to thank the director of the core center of South Korean University for having collaborated with us. It is imperative that we continue to invest in research and development area to create a cleaner and greener future. I am very happy to inform that our beloved Chancellor has announced ₹7 crores for the benefit of this research in this university. The environment is major area where nanotechnology can make a significant difference. They offer innovative solutions to mitigate pollution, reduce environmental impact, and promote sustainability. Our collective responsibility is to harness these capabilities to safeguard our planet for future generation, one of our sustainable development goals, what nation expects. I encourage researchers, scientists, and innovators from India, South Korea, Thailand, USA, Canada, and United Arab Emirates to continue their pioneering work in this field. I am very much thankful to the organizers, particularly my colleague Professor Dr. V. Anbalagan, the convener of the conference, and his entire team for organizing this mega event in physical form. I am confident that this conference for coming 2 days will yield valuable insights and collaborations that will propel us towards a brighter and more sustainable future. We expect some good outcome of these research articles which can end in the form of product or in the form of any other research projects which can save the nation. Thank you once again.
Thank you so much for your valuable speech and guidance, sir. Energy and persistence conquer all things. Now we take the privilege for inviting the Dean of Vinayaka Mission's Kirupananda Variyar Medical College and Hospital, Salem, who has been a pioneer in the field of medicine, per se in the field of ophthalmology, having 3 decades of experience, and who also proves to be an administrative excellence. His works has been published in various articles. He has been awarded with the Best Administrator Award, CM Dr. MGR Award, Lifetime Achievement Award, Exceptional Faculty of Medicine Award, and many more, adding more golden feathers to his crown. We take immense pleasure in welcoming Professor Dr. K. L. Vedan sir to felicitate the gathering.
The most respected chief guest of today's function and today's conference, Sri N.V. Chandrasekhar, Vice President of Vinayaka Mission Research Foundation, the guest of honor, Professor Mayang Gyong Chai from South Korea, and the Director of Vinayaka Mission Research Foundation, N.R. Ramasamy sir, most honorable and respected Vice Chancellor, Professor P.K. Sudhisha, honorable and respected Registrar, Professor Nagapan sir, and lot of guests from Thailand and Korean guest speakers and faculties, and today's hero of this function, Professor Anbaragan sir, and his entire team is conducting a Indo-South Africa Thailand 3rd International Conference about Nanoscience and Nanotechnology for Energy, Environment and Biomedical Applications. It's immense pleasure to welcome you all to this Vinayaka Missions Research Foundation, and particularly is jointly organized by Vinayaka Missions Kirupananda Variyar Arts and Science College. I was really, to be very honest, I was very shocked to see that. It says I just discussed with the Professor Anbaragan for past few days, who works with Professor Das sir, who has come and conducting the function. I was wondering, there's nanoscience and nanotechnology. What, up to my knowledge as a doctor, I was only the engineering college and this technology people as conducting a nanotechnology and nanoscience for this kind of conference. It is really, really happy that the Arts and Science College is conducting the 3rd international conference in this offline this period. It is really, really wonderful, this achievement. Give him a big applause to Professor Anbaragan sir for his wonderful achievement. This is a great pride for the Vinayaka Mission Research Foundation to welcome for this outstanding topic of nanoscience and nanotechnology. As a doctor and as a medical field, we wanted this nanotechnology and nanoscience. Whatever the collaboration is biomedical technology, it's going to be the future in this world. And is also the artificial intelligence and nanotechnology is going to occupy the entire world in another 50 years. I request many people and many speakers and many innovative research of young engineering as well as arts and science and the field of nanoscience technology guys to just innovate this idea and welcome to this Vinayaka Mission Research Foundation for lot of ideas and come this that. You know all of this for the guest speakers of South Africa, South Korea and this Thailand. The Vinayaka Mission Research Foundation is, as he said, we are concentrating, we are growing and progressing. We are giving us a lot of funds to this research foundation and research aspects. Because of that, we found as the Ganeshan Incubation Center and all this. We welcome the researchers and is giving speakers to this wonderful conference. Once again, I congratulate the entire team, organizing team of this Vinayaka Missions Kirupananda Variyar Arts and Science, and a big round of applause to them one more time. Thank you, sir.
Thank you.
Sir is a professor of chemistry, Gyeongsang, National University, Republic of Korea. He has done his PhD in chemistry from University of North Carolina at Chapel Hill, USA in the year 2006. He had received a number of national and international awards, which includes Top 50 Environmental Technology Award by Ministry of Environment 2014, KCS Young Physical Chemist Award 2015, the Garchuk Award for Excellence in Teaching 2016, member of Garchuk Hanlin Academy 2020. We are honored to have you with us, sir. Now I welcome Dr. Myong-Young Choi, convener INEEBA-2023, Director, Co-Facility Center for Photochemistry and Nanomaterials, RINS Gyeongsang National University, South Korea. I invite sir to bring the conference highlights into limelight.
Okay, thank you. Good morning to all attendees and present here, or good afternoon, those especially in Korea this afternoon online. On behalf of the Core Facility Center and Photochemistry and Nanomaterials at Gyeongsang National University in South Korea, it is my privilege to extend a warm welcome to each and every participant of this international conference. I'm deeply honored to co-organize the 3rd Indo-South Korea-Thailand International Conference on Nanoscience and Nanotechnology for Energy, Environment, and Biomedical Applications, INEEBA-2023. This event is a result of collaborative endeavor involving Vinayaka Missions, Kirupananda, Variyar, Arts and Science College, a constituent college of the Vinayaka Missions Research Foundation, deemed to be a university in Salem, and Chulalongkorn University in Thailand. Today, I'm very happy to be able to attend this conference in person, and following 2 years of virtual participations in both inaugural and subsequent meetings due to the COVID-19 pandemic. And this transition from virtual to physical attendance not only signifies the resilience of our scientific community in these challenging times, but also underscores the increasing importance of this conference series as a cornerstone for research in nanoscience and nanotechnology for energy, environment, and biomedical applications. The objective of INEEBA-20 and 23 is to serve as an efficient platform for academicians, researchers, and startups, and industrial participants to connect, discuss, and exchange their research ideas and explore appropriate future strategy in the field of nanoscience and nanotechnology. Furthermore, the conference is designed to offer young scholars an opportunity to refine and augment their research capabilities with a particular focus on development and applications of cost-effective smart materials for future generations of researchers. INEEBA 20 and 23 features 4 technical sessions and 2 keynote lectures and 12 invited talks, diverse by distinguished speakers. We are pleased to host approximately 400 contributed papers from diverse nations, including India, South Korea, and Thailand, and the United States, Saudi Arabia, and the United Arab Emirates, and Canada. And these contributions will be showcased in 6 parallel oral sessions and conducted in both in-person and virtually. So recognizing the contributions of young researchers is integral to the advancements of scientific community. So to this end, INEEBA 2023 will be awarding the Best Presentation Awards to commend young scientists who have exhibited a strong commitment to R&D and produce high-quality research. Before closing, I must express my profound gratitude to Vinayaka Missions Research Foundation Management and Chulalongkorn University for their invaluable support in organizing this wonderful conference. The vision of Gyeongsang National University is to keep pace with the world active GNU. So one of the goals of our institution is to strive for excellence in research specializations and blending. So I strongly believe that this INEEBA 2023 is one of the outcomes of the goal of our university, which is also in line with our vision. It's truly delighting to be part of this conference. I'm confident that the collaborations fostered through this conference will serve as a catalyst for furthering research partnership among the participating institutions. So let us all engage in this enlightening expedition and leveraging this online and offline platform for the exchange of knowledge and enhancements of research collaborations and networking. And also I must thank Dr. Ambalagan for organizing a wonderful conference. Join me thanking Dr. Ambalagan and for a wonderful conference. And thank you very much all. Thank you.
Thank you so much, sir, for dwelling us with your ton loads of knowledge. Thank you, sir. We are drowning in information while starving for wisdom. The world henceforth will be run by synthesizers, people able to put together the right information at the right time, think critically about it, and make important choices wisely. He is a leading academician, administrator, and researcher in the field of homeopathy and health sciences. He did his BHMS and MD Homeopathy from the Government Homeopathy Medical College, Calicut, Kerala, India. Under the University of Calicut, incidentally, he became the first resident MD rank holder in homeopathy, 1995, India. He is having more than 3 decades of professional experience and more than 2 decades of academic and administrative experience in the field of homeopathy and health sciences. Previously, he was the Controller of Examination in Kerala for 8 years in the University of Health Sciences, Thrissur, as the Founder Controller of Examination of KUHS. Sir has introduced many digital examination in health sciences disciplines. He has published various scientific articles in national and international journals. He has been awarded Dr. Mahendra Singh Memorial Best Administrator Award, Kolkata in 2014, National Rejoice Ayush Award, New Delhi in 2019. Currently, Sir is the Vice Chancellor of Vinayaka Missions Research Foundation, deemed to be university. It's my honor to welcome our Honorable Vice Chancellor, Dr. P.K. Sudhir Sir, making it possible to attend this function despite his busy schedule. We request Sir to address the gathering. Over to you, Sir.
Respected Chief Guest of this today's function, Sri N.V. Chandrasekhar, our Vice President of VMRF DU. Respected Guest of Honor of today's function, Professor Dr. Myong Choi, the Director, Gyeongsang National University, South Korea, our Director, N.R. Ramaswamy, our Registrar, Professor Nagapan, Dean VMKB Medical College, Dr. Elil Venden, honored and invited guests from Thailand and Korea, Head of the institutions of VMRF DU, Constituent colleges, special invitees, Head of the departments, faculty members, participants, delegates who are joined online, ladies and gentlemen, a very, very good morning to you all. I welcome once again to the hall the people, this Indo-South Korea-Thailand 3rd International Conference on Nanoscience and Nanotechnology for Energy, Environment and Biomedical Applications. At the outset, I congratulate the organizers for taking this wonderful initiative, especially our Dr. Anbergen and the Principal of Arts and Science College and his entire team. It is a proud moment for me to preside over this function, which is being organized by our Vinayaka Missions Kirupananda Variyar Arts and Science College, a constituent college of Vinayaka Mission Research Foundation deemed university for the 3rd time, in joint collaboration with the Core Facility Center for Photochemistry, Nanomaterials, Gyeongsang National University, South Korea, and Faculty of Engineering, Chulalongkorn University, Thailand. The organizers have harvested great success in 2 grand events previously, 21 and 22, or the online mode. Many high quality scientific papers were published in reputed international journals as a special issues in the Springler and Elsevier publishers. In addition, our Vinayaka Mission Research Foundation deemed university has entered Memorandum of Understanding with Core Facility Center for Photochemistry and Nanomaterials, Gyeongsang National University, South Korea. This shows the constant and tireless efforts taken by organizing team in bringing out the fruitful essence through these mega events. With the same spirit of the organizing committee, I even hope that this 3rd International Conference of INEEBA-2023 may cover the many diverse fields in nanoscience and nanotechnology for different applications. I understand there are more than 400 participants for this conference who are physically present, and people are joined online from around 16 states from the country, and also more than 6 countries outside India. Delegates are participating from 16 states, and there are 220 oral presentations and 30 poster presentations. In this pursuit of the nano frontier, researchers, scientists and engineers from around the world have come together to share their knowledge, discoveries and innovations. Nanoscience has opened new avenues for understanding the fundamental building blocks of matter, from ultra-efficient solar cells to targeted drug delivery system, and the possibilities are endless. However, With great potential comes great responsibility. As we delve deeper into the realm of nano, we must also be mindful of the ethical, environmental, and safety consideration that come with these advancements. I hope this conference will surely guide you towards the future application of nanoscience and nanotechnology. Vinayaka Mission Research Foundation deemed university is very serious on research, innovation, and collaborations with reputed institutions and universities within India and abroad. And last couple of years, our focus was very strong in these areas, and we started yielding results in terms of journal scientific publications, patent applications, and extramural funding from the competent authorities. I am extremely happy that our university is jointly presenting this conference the third time with a very specific focus. Once again, I want to express my deep appreciation to all the participants, speakers, and especially the conference organizers who have made this conference very meaningfully possible. I encourage you to make the most of this opportunity to engage with your peers, to learn from the best minds in the field, and to contribute your own insights and discoveries. Let us work together to find the incredible potential of nanoscience and nanotechnology for the betterment of humanity. I am sure there will be a very meaningful deliberations in the domain, in the topic chosen in the coming 2 days, and I am sure there will be a very strong takeaway for the participants who are joined physically or also who are joined online from this conference. I wish a very, very meaningful deliberations in the coming 2 days, and wish a very comfortable stay in Salem who are physically joined here. Thank you very much.
Thank you, sir, for sharing your words of wisdom and experience.
Coming together is a beginning. Keeping together is a progress. Working together is a success. The world is a mosaic of ideas, and together we complete the puzzles of progress. It's a memorable moment to release our international conference proceedings. May I request Sri N.V. Chandrasekhar sir to release the proceedings to our Vice Chancellor sir. Thank you so much, sir.
Be thankful for what we have. You'll end up having more. If you concentrate on what you don't have, you will never ever have enough. He is a man of sincerity, dedication, hard work. With all due respect, he possesses two decades of teaching experiences. It's our pleasure to invite Head Department of Computer Science of Vinayaka Mission's Kirupananda Variyar Arts and Science College, Dr. M. Prakash sir, to deliver a vote of thanks.
A very good morning to all. With great pleasure and a profound sense of gratitude, I stand before you today to deliver vote of thanks for this inaugural session of our esteemed international conference in INEEBA 2023. We are truly honored and humbled by your presence, and I would like to extend our deepest appreciation to all those who have made this event possible in successful way. First and foremost, I would like to express our sincere gratitude to our distinguished chief guest, Honorable Sri N.V. Chandrasekhar sir, Vice President, Vinayaka Missions Research Foundation, deemed to be university. Then I would like to express our sincere gratitude to our distinguished guest, Honorable Sri N. Ramasamy sir, Director, Vinayaka Missions Research Foundation, deemed to be university. Then I would like to express our sincere gratitude to our distinguished guest of honor and keynote speaker, Professor Dr. Myang Choi, Director, Core Facility Center for Photochemistry and Nanomaterials, RINS, Gyeongsang National University, South Korea, who have graced this occasion with their wisdom, insight and expertise. Your presence has added immense value to the inaugural session, and your words of inspiration have to set tone for the rest of the conference, sir. Once again, thank you, sir. And then I would like to express our sincere gratitude to our Honorable Vice Chancellor, Professor Dr. P.K. Sudhir, Vinayaka Mission Research Foundation, deemed to be university. Once again, thank you, sir. And then I would like to express our heartfelt gratitude to our respected Registrar, Professor Dr. Nagapan sir, Vinayaka Missions Research Foundation, deemed to be university. Then I would like to express our sincere thankfulness to our respected Dean, Professor Dr. L. Vendan sir, Vinayaka Missions, Kirupananda Variyar Medical College and Hospitals. Then I extend my sincere thanks to Professor Anangnat Songwang Dhanraj, Associate Dean, Department of Chemical Engineering, Faculty of Engineering, Chulalongkorn University, Thailand. Then I would like to extend my heartfelt gratitude to Professor Manunya Okavilai, Scientist, Metallurgy and Materials, Science Research Institute, Chulalongkorn University, Thailand. Then I would like to thank Professor Manansi Sutipong, Assistant Professor, Department of Chemical Technology, Faculty of Science, Chulalongkorn University, Thailand. I extend my sincere thanks to Professor Vanvisa Limprat, Synchrone Light Research Institute in Thailand. Then I would like to thank Jeon Park, Department of Chemistry Research Institute of Natural Science, GNU, South Korea. I would like to thank Professor Dr. J. Tirthagiri sir, Senior Scientist, Brainful Fellow, Core Facility Center for Photochemistry and Nanomaterials, Research Institute of Natural Science, Gyeongsang National University, Republic of Korea. A special thankfulness to our respected principal, Professor Dr. V. Anbalagan sir, who took this opportunity to this international conference to be a success. He invited delegates to show their presence and motivate us to participate in this conference. Then we would like to thank our organizing committee and all the delegates, individuals who have worked tirelessly to plan and execute this conference. Your dedication and hard work and attention to detail are function upon which this event has been built. And then I would like to thank Dr. Babyjan sir, Dean of Vinayaka Mission Kirupananda Variyar, Vinayaka Mission Sankaracharya Dental College. And then I would like to thank Dr. Anbuchalian, Principal Annapurna Engineering College. And then I would like to thank Dr. Surya Narayanan, Deputy Director, Vinayaka Mission Research Foundation, deemed to be University Research Department. Our institutional and residents participants, thank you for joining us from various corners of the globe. Your presence here today signifies the importance of the topic and themes we will explore during this conference. We look forward to exchange of ideas and rich discussion that will undoubtedly essence ever coming days. We would like to acknowledge support of the venue staff, technical team and all those who have contributed to the smooth operation of this event. Your professionalism and dedication have not gone unnoticed. Last but certainly not least, a heartfelt thank to you all the audience, both here and those joined virtually. Your enthusiasm and encouragement are the driving force behind this conference. Your active participation will ensure that the knowledge shared and connections made here will have a lasting impact of our respective fields. Once again, on behalf of the organizing committee, all those who have involved, thank you for being part of this Moments International Conference. We look forward to the enlightening session and meaningful interaction on the lie ahead. Thank you, and let conference proceeding begin. Thank you for opportunity given. Thank you one and all.
Thank you, sir, for your valuable words. It's always important to know when something has reached its end. It's been a pleasure being with all of you today. Thank you all for your patience. Thank you once again.
The power of national anthem unites us and fills our hearts with love for our country. I kindly request all to stand for the national anthem.
Memento, that one.
I request all the participants to occupy the seats. I request all the participants to occupy the seats. Let us start with the presentation session now.
Hello, check.
Check.
Maybe. Oh yeah, it's okay. It's all. Maybe you can use the microphone.
We'll be shortly starting with the keynote lecture. I request the delegates to settle down as soon as possible.
Yeah, it's working. It's working.
Check. Keynote lecture will be given by Professor Dr. Myo-Young Choi, Director, Core Facility Center for Photochemistry and Nanomaterials,
Hello.
Research Institute of Natural Science, RINS, Gyeongsang, National University, Republic of Korea. The title of the session will be Pulse Laser Induced Synthesis of Clean Energy Materials.
This session will be chaired by Professor Dr. Deepthi Shastri Ma'am, Deputy Dean, Vinayaka Missions Kirupananda Variyar Medical College and Hospital, Salem. Over to you, sir.
Yeah, it's working. It's a battery problem.
You already invited me? Yes, yes, Good morning, everyone. I deem it a privilege to introduce the first speaker of the day in the Indo-South Korea-Thailand 3rd International Conference on Nanoscience and Nanotechnology for Energy, Environment and Biomedical Applications, Professor Dr. Myung-Young Choi. Professor Dr. Myung-Young Choi is a physical chemist specializing in spectroscopy, laser photochemistry and nanomaterials. He is a senior academic staff member at the Department of Chemistry at Gyeongsang National University, South Korea, where he teaches both UG and PG students. In addition to his teaching duties, he serves as the director of the Core Facility Center for Photochemistry and Nanomaterials. He has earned his MS and PhD in chemistry from the University of Idaho and the University of North Carolina at Chapel Hill, USA, respectively. After his studies, he worked as a postdoctoral fellow at the Faculty of Science, University of Southern California, USA. He also had the opportunity to serve as a visiting professor at the University of North Carolina at Chapel Hill between 2013 and 2014. His research team has developed numerous innovative techniques based on laser processes to characterize and produce a variety of metal nanoparticles, alloys, composites, and coordination polymers. Their significant contributions to spectroscopy sensor technology and catalysis are well recognized. Recently, they have also been involved in the laser synthesis of functional nano and biomaterials for use in energy production and environment remediation. Professor Chui has held several editorial positions in prestigious journals, including senior editor for the Journal of Laser Applications, editor for Light, Science and Applications, and associate editor for Environmental Chemistry Letters, Applied Nanoscience, Chemistry Papers, and Alexandria Engineering Journal. He has also served on the editorial board for the Journal of Hazardous Materials and Bioengineer, and as a guest editor for Chemosphere, Environmental Research, Biomass Conversion and Biorefinery and Environmental Pollution journals. He has edited a book titled Oxide-Free Nanomaterials for Energy Storage and Conversion Applications for Elsevier, and is currently editing another book titled Pulsed Laser-Induced Nanostructures in Liquids for Energy and Environmental Applications for the same publisher. Professor Chui's scholarly output is impressive, with over 200 referred papers published in high-impact international journals, 4 book chapters, and 6 patents to his credit. He has delivered several invited keynote and plenary lectures at international conferences and academic institutions. He has served on several management committees at Gyeongsang National University, including as the director of the Center for Lab Safety, the director of the Center for Research Facilities, and the department chairperson. He has also served on the scientific advisory boards of external scientific organizations. His work has been recognized with several prizes, awards and fellowships, including membership in the Gyeongsang Hanlim Academy, the Gyeongsang Award for Excellence in Teaching, the KCS Young Physical Chemist Award, and the Top 50 Environmental Technology Award by the Ministry of Environment in 2014. We are fortunate to have an internationally acclaimed speaker in Professor Dr. Myung-Young Choi. Please join me in extending a warm welcome to the speaker by a warm round of applause as we invite him to take the podium.
Thank you.
Thank you
very much. Thank you very much for your wonderful introduction, and thank you for all here, and very honored to give a invited keynote talk in INEEBA-2023. And my title of this talk is First Laser-Induced Synthesis of Clean Energy Materials. I'm sorry that it's my, the laser point is not working because of the LED, so excuse me. And thank you all, and also today is a national holiday also in Korea too. So those Korean, people, watching YouTube or, this online platform, and I wish you all the best for the Chuseok holidays. And also thank you for all people coming here too. And I'm Myung-Young Choi. I was introduced by from Department of Chemistry, Gyeongsang National University in South Korea. This is the viewpoint of the Gyeongsang National University, and the center is the one that we are located in Gyeongsang National University. So before I go, so this is the world map that the South Korea, where my hometown is located, is very southern part of South Korea, and Bangkok, and it's a Salem here in the Vinayaka missions. And this is the wonderful conference, the collaborative research conference started from 3 years ago. And this is the view of the Jinju, where my hometown is. You can see this Jinju fortress. It's a beautiful scene in autumn season. It'll be now in Korea. It's autumn. It's very like about 20 to 25 degrees, and you can see the night views of Korea. So you are welcome to come to Korea whenever have a chance to come to Korea. Just so you can email or just contact us. And this is the another viewpoint of the Gyeongsang National University, and that building, the center, that's where the core facility center is located. And here another world map. I came from Jinju to Incheon to New Delhi to here Salem, and I'm going also back to the Chennai and to the Singapore to Incheon and Jinju. So this is a complex. So I like to one day to be a direct flight from Salem to my hometown would be much better. So people like simple things. I like a simple life and very like it. So it applies to my facility center to make the complex system to simpler systems. So I made it all this equipment or apparatus in one site and one-step experiment. So students, researchers working and doing their experiments, and in laser room and open lab, they're synthesizing and making materials. You can go to the like a 10 steps. You can get the SEM images and XPSs, and the next building is TEMs, and all facility for photochemistry and nanomaterials are available. So it's easier and a much simpler system and environment for my core facility center. And here's mostly more than 30 specialized instruments for the photochemistry and nanomaterials. And mostly we're working on site, so much easier and much simpler experiments we can do for the photochemistry and nanomaterial. So here's the real view, real images of photochemistry lab or core facility center. You can see the laser systems and FSM, XPS, and XRDs, all things, and also in situ experiments. So you can measure all the ongoing reactions by using the in situ instruments. And it's mostly specialized in situ multispectral analysis and multi-spectroscopic tools in the droplets of levitated droplets, and the FSMs and XPS and low temperature. It goes down to about 10 Kelvin. So what I like to explain my brief history, and I started from helium, 0.4 K helium nanodroplets, and going for the gas-phase spectroscopy, and also using the lasers to synthesize the nanomaterials and applies to the all electrochemical or HEL, hydrogen evolution reactions and oxygen evolution reactions and all kind of things. I like to merge it using the acoustic levitator, so that we can study on-site and also in situ studies of the reactions during the chemical reactions, and we can measure, you can study, characterize the mechanisms. So based on my spectroscopic background, and here's I majored in physical chemistry, laser gas-phase spectroscopy, and using the all different kinds of equipments. And I like building lots of different spectroscopic instruments, and also a lot of things we are interested in. And here's a brief view of my lab, and using several different kinds of lasers in high vacuum chambers, doing several spectroscopic tools that's in physical chemistry book. And this is a real view of one of my labs, and using the all different kinds of lasers in high vacuum chamber for excited state measurements. And the one that I mentioned before, now I'm interested in in-situ spectroscopic tool. It's called the acoustic levitator. here is a real view of the images. And you can see that, droplets here, this is the droplet is floating. So by using the acoustic levitator, and we can shine all different kinds of light sources, UV, IR, Raman, and thermal, and you can think of in temperature control things, all these things one time, one step. So we can measure because there's a wall-less, there's no wall. So you can think of chemistry as a wall in like a beaker or other things, but we don't have a wall. So we can have all different kinds of lights going through that droplet, so we can measure at the same time as the reaction goes. So you can see that here's the in-situ Raman as reaction goes, in-situ visible, UV visible, and FTIR, all things one droplet, so one time, and in-situ reactions we are interested in. So to study the mechanism of the reactions, what we are doing. And so here's the Trian Park is going to presenting he's an expert on in-situ monitoring of the reactions in acoustic levitator. Please welcome to hear his lecture. And the mission of my lab or co-facilitator is building a world-class energy, environment, and sensor, specialized center. And we use all different kinds of lights, like including lasers and solar lights and microwaves, and using these lights to synthesize nanomaterials. And then we can apply all these kinds of on-site characterizations in the center, and we can apply this to the renewable energy and environment, and photocatalysis, and also green chemistry, and now very hot topic nowadays. And so let me go on to the details. This is the kind of laser-assisted synthesis using lasers, mostly top-down approaches and bottom-up approaches. Top-down is like breaking down the large pieces of material of nanoparticles and synthesizing. And this is called pulse laser ablation in liquids, PLAL. And the other thing is bottom-up approach. We can reduce the metal ions to the metal nanoparticles. So using lasers, we call this pulse laser irradiation in liquids, PLIL. So using this, you can see the real-time video of the pulse laser ablation. And the upper one is gold nanoparticles, silver nanoparticles. So it's really fast, rapid process, and less complexity. So I like simple ones. So no, surfactants, no reducing agents. So it's like a product-free and eco-friendly synthesis. So we don't have to use heat to synthesize nanomaterials. So using in ambient temperature, using the applied laser systems. So we produced various morphological nanoparticles and applied to the various different kinds of applications in my lab. So first thing I'd like to talk about this is using the nickel nanoparticles. As you know, nickel has FCC, the phase center cubic, as a global, the stable state structure, and a metastable one is a hexagonal close-packed HCP structures. So we use laser to synthesize nickel nanoparticles. We have all different kinds of phase differences in XRD spectra, here. So you can see that depending on the solvents we use, 4 different kinds of solvents, and DI water produces nickel oxide, methanol, and hexane, acetonitrile, all different kinds of 2 different kinds of phases are formed. But we use secondary ablation after the first ablation. You can see that there's only FCC and formed in the methanol and hexane, but in acetonitrile case, the metastable HCPs are formed. So it's very selective synthesis using the laser for nickel nanoparticles. So we thought that maybe this is due to the like a specific heat of solvents plays very important role in maybe in thermodynamically or kinetically in the cooling process of plasma plume. So I spent some time on it because we didn't know what to expect. So there's thing that only changes with some trend is specific heats are different. So I set up another system, laser ablation process. So we are interested in looking at the plasma plumes so that the nanoparticles are formed in the plasma plumes. So using the ICCD camera, using 1064 nanometer pulse laser. And you can see that this is the time sequences of pulse laser ablation process. And at 0 time, a laser shines, and then plasma plume happens at around 400 nanoseconds. Later on, a shock wave forms about 200 seconds later and dies away at about 5 or 6 microseconds. And light spot formations about 1 microsecond. And the thing we are interested in is a cavitation bubble starts from 1 microseconds to 500 microseconds. So in this region, you can see white thing, not clearly, but that's nanoparticles formed in the plasma plume. So what we did is, you can see all different cavitation bubble studies. It's clear to see that in methanol, only HCPs are formed, and acetonitrile, these HCPs are formed. So, and you can see that this is in a acetonitrile case, it has the lowest specific heat. So you can see that dramatic volume changes. Volume changes really fast comparing to the methanol case, so that it cools down the formations of nanoparticles, so that the metastable forms are happened, and in the slow cooling in methanol case only the stable FCCs are formed. And also we tried it with a one-part laser synthesis. There's the nickel nanoparticles also formed, and also the carbon layers from the solvents. So we shined one shot, and formed nanoparticles with the carbon layers from the solvent decompositions. So you can see, you cannot clearly see, but over there, there's this spacing of 3.35 angstrom, which is in good agreement with the graphite carbon. So this is what we suggested as mechanism is when you shine the laser, solvents are decomposed, and then there are 4 different kinds of morphological and nickel nanoparticles are formed. In hexane case, graphite carbons from the solvent, and because acetonitrile has a nitrogen, so the nitrogen doped carbon layers form onto the nickel nanoparticles. So we use 4 different solvents. It's 2 upper is no carbon layers, because DI, water, and methanol, there's no carbon layer. But in hexane or acetonitrile case, we have carbon layers. So that you applied it to the lower part over there. This is a methanol and DI water, shows catalytic efficiency because gold nanoparticle has catalytic activity. But the other 2 down, because of the productive carbon layers, the catalytic efficiency is very less. But in opposite case, we use the strong acid to dissolve like a nickel nanoparticles. As you know, the metal nanoparticles are dissolved in strong acid. So as you can see that there's no carbon layer, so they dissolve in this here. So with the acid, but here with hexane and acetonitrile case, they survived because of the productive carbon layers. And also you apply to this gold nanoparticle, and we control the gap between the gold nanoparticles with number of graphite carbon layer by controlling the ratio of solvent mixture So as I mentioned before, and acetonitrile produces a carbon layer. Water, no carbon layer. So we mix together the ratio so that we can control the gap, number of gaps, so that we can control the gap distance between two gold nanoparticles, so that we can apply this to the surface enhancement of Raman scattering, as you all know, the Raman. And we apply this one to the nitrobenzothiool or 4-aminobenzothiool. We apply this one to the theoretical calculations. You can see the hot spot in acetonitrile, 30 case. 30% of acetonitrile and 70% of water. Then the optical gap was found to be about 1.4 nanometers size. And another system that we tried it, we used the urea for the nitrogen source. So nitrogen doped zinc oxide on silver for catalytic applications, and we did lots of characterizations, and we showed that photocatalytic efficiency or activity of rhodamine B showed 98% of degradation on the solar light in 90 minutes. And also similarly to that, we use a laser to synthesize zinc oxide and onto the gold. On the also the RGO, reduced graphitic graphic oxide, and also C3 and 4 nanocomposites. So this one also shows onto the RGO5 weight percent shows the best efficiency, and here 15% of gold weight percent and 20% of gold weight C3 and 4 showed 99% within 120 minutes on the solar light irradiations. And so then what happens to the copper? So it's a little different. You remember, the DI water and methanol, hexane, and acetonitrile, they all have spherical nanoparticles and graphitic carbon layers. But in this case, a methanol as a carbon oxide nanorods are formed, and acetonitrile is the copper cyanide group formed metalloorganic complexes. So depending on the four different solvents we applied to the reduction of aromatic nitro compounds. We use copper oxide nanorod to reduce the 4-nitrophenol to the 4-aminophenol, and copper graphitic carbon, the third one in hexane, it shows the aniline reductions. So this is another simple system we apply in the photocatalytic, or catalytic, copper-based catalytic. And you see that which one was the first one, DI water, and we use DI water to synthesize copper and coarser copper to oxide nanoparticles. So we characterized on-site experiments and apply to the nitride reduction, and to generate nitride, the pollutant, to the value-added ammonia. So in this case, and also we used laser system in methanol with sonicator. So sonochemistry happens again in gold and platinum alloys for hydrogen oxidations. So we use gold and platinum, and this one actually, Dr. Thitagiri is an expert, so he's going to tell you about all the different stories for hydrogen-coupled water electrolysis. And simply, this is overall water splitting is just like producing oxygen and hydrogen. And for the oxygen case, OER, the oxygen evolution reaction, has high theoretical potential, 1.23 volts. But the hydrogen-coupled oxidation reduction is required much less, so that less energy, less powers to generate the hydrogen. So it's a much simpler system and also cost-efficient system for using the hydrogen copper water electrolysis. So Dr. Ditagiri will tell you about more in detail. And similarly to this one too, this is energy saving hydrogen production at low cell voltage. So we don't have to use high voltage. So we use less voltage to generate OER and hydrogen productions. So similarly, we use a copper or cobalt onto the on the target, and then using the palladium salt solution to reduce to make the palladium nanoparticles. So cobalt and the copper palladium alloys. So we applied this one to hydrogen, cost-effective nano materials. So in other cases too, here nickel, cobalt, copper. So I mentioned the nickel and cobalt and copper. So using the benzo tricarboxylic acid and BTC. So using three different metal sources. You have a copper and cobalt and nickel upper part there, and different shapes like copper case octahedral structure, and cobalt case hexagonal structure, and nickel seed-like structures, all different shapes. And we all characterized it and also did electrochemical analysis and applications, and we found that cobalt BTC shows the best efficiency in HER and OER and overall water splitting case, because the cobalt has very large available cobalt active center and various oxidation states, cobalt 2+, 3+. So this is the one. So it's been published in Chemical Engineering Journal. And another one, it's been published in HS Nano featured at the carbon image, was we shined the laser to the MXene. MXene is a TI 3C2TX. So multiple layers of MXene, we shined the laser, and we reformed core shell structure with one part. One laser shot, it formed like core shell, TIC inside and titanium oxide and platinum coated on it. So we did electrocatalysis HER and showed a superior and excellent HER hydrogen production with excellent stability about more than 50 hours. And then we use sunlight, 1.5 AFM sunlight, and also this one showed even better with PTC here. I cannot clearly see here, even higher than the commercial PTC catalysis. So this is the one that we are working on using the MXene system. And another one we applied to this MXene and using the microwave synthesis. So we have different kinds of high entropy oxide. So this is a type of multiple oxide, contains 5 or more than 5 metal cations. So this one also showed photocatalytic, photo and electrocatalytic OER. And this is for the OER case, commercially available iridium oxide is comparable with a high stability too. So it's featured in small cover. And another one we are interested in is alloys. And high entropy alloy has alloy that contains more than 5 metals, so that we did all in-situ Raman. So when we do the electrophotochemical, reactions, we measure in-situ, just like a time-dependent experiment. So we found that the intermediates. So what are the intermediates? So playing role in these reactions. So we find it, and you can not clearly see, but here is a 2 nanometer sized nanoparticles onto the carbon nanotubes. And another one we use a laser, transition metal carbides, TMC. So as I mentioned, laser decompose the solvents. So decompose the solvents, and then we can make a metal ionizations, like from metal plates to the so that solvent decomposition and metal atomization combination produces a transition metal carbides, like cobalt, iron, titanium, molybdenum carbide. This one also will be explained well by the Dr. Giri. And it's a much simpler system. So we don't have to use heat and other things to shine the laser, and we found it is easily formed. Otherwise, it is really hard to form these kind of carbides. And also applies to the HER and OER. And using the in situ Raman, we found the activity sites for the OER. And so we explained how the reaction went. And another system that we use is copper BTC that I mentioned before. It's copper oxide with a carbon, or ruthenium oxide with a carbon, pulse laser ablation in liquid. And so this one showed this one also will be explained by Dr. Giri, is experts in the electrocatalytic reactions. So it shows good reactions for fural oxidations. So it this one recently published in Applied Catalysis B, Environmental. And another one that we're using is a ZIP69 polyhedral. And we use a laser, and also you can use calcination process, and also oxidation, the ion exchange, so that we synthesize iridium, cobalt oxide, and nitrogen doped carbon layer. So it even shows also the best overall water splitting applications, and by characterizing the all issue the Raman. And the last or the least, the dual laser systems. So we use now two laser systems to make a graphene oxide to the what's called the reduced graphene oxide, and also synthesizing cobalt, the hydroxide. So we by characterizing in situ Raman, so we could understand that cobalt oxo hydroxide and cobalt oxide are reductive intermediates in our system too. So it's published in ECOMED recently, and so that by summarizing my research, so my lab is mostly focusing on the lights, the laser, or other things, microwave or any light sources, and to generate all different kinds of materials and laser-induced materials, and applies to the electrochemistry, the energy and the environment, and sensor systems in my lab. So if you're interested in this review paper, shows very fundamental understanding of laser processes. So you can refer to these light science applications. And the last, my lab in 2023, this year, mostly we were working on sensors and photocatalysis and spectroscopy, but mostly many people now is working on electrocatalysis in my lab. So that if you're interested, please visit my homepage, and this is my choice lab at .gnu.ac.kr. And I'd like to thank, I have lots of international collaborators, but I cannot show in here, but too many. And but I have to thank my lab members, doctors and PhDs and masters, undergrads, and I'd like to thank all the research funding sources for this research. And also, thank you very much for your kind attention. Thank you.
Thank you, sir, for your scintillating talk. We appreciate the extensive work that you have done and amazing work that you have done in synthesis of nanoparticles, which are clean energy materials. The session is open for discussion. If you all have any queries, please ask the speaker.
Sir, good afternoon, sir. So thank you very much for giving a wonderful lecture, sir, about your laboratory and research activities. So I have a fundamental question, sir. So you are talking about preparation of nanoparticles through laser ablation. So how the laser light can generate or prepare particles of dimension? Generally, nanoparticles should have dimension of 1 to 100 nanometer size. So how it is creating? Can you give more insight on that?
Okay, thank you very much for your nice and excellent question. And this is a fundamental, laser-induced synthesis. So it also depends on the parameters of lasers and also solvents and other material itself. But generally, so what we say in laser-induced synthesis using laser is we shine the laser using the focusing lens. This first ablation process. Without lens is irradiation process. It's the laser goes through and then reduce the metal ions to these metal nanoparticles. But focusing lots of energy. So laser goes onto the surface here, and when it focuses to this, as I showed before, plasma plumes happens. So at that point, the very harsh conditions, about 500 to 600 Kelvin temperature, and also several gigapascal, high temperature, high pressure conditions. So the laser produces metal ions. So ions, and then they cools down in cavitation bubbles, and it reduces and make it atomizations and also clusters and nanoparticles. But depending on the system you will use, 100 or several nanometer sizes or micron sizes. So depending on the parameters we use in the system, and also material itself. So that's the thing. It's very common in laser-assisted synthesis, and that's well explained in our review papers and other review papers in the world. Okay. Thank you for your questions.
Registrar sir would like to ask a question. Can you please pass the mic to him?
How high is this Raman synthesis in your process?
How high?
High is this Raman synthesis?
Raman
synthesis. You are using Raman synthesis, isn't it?
Oh no, actually we characterize using Raman, but we mostly using laser. For the Raman, it's using laser and to excite it to the virtual state, and it goes down to the ground state, and then sketch. We can see the gap between the initial and final stage. But here we use a laser onto the surface of metal nanoparticles, metal plates, to make the plasma plume at high temperature, high pressure, and ions come.
Yeah, how high it is?
Oh, it's about people saying experimentally 5,000 or 6,000, 1,000 Kelvin.
Yeah.
Very high temperature and high
that's what
pressure.
Yeah.
Okay, Raman is for the characterization.
Yeah.
Okay. Thank you.
Anybody else?
Professor, thank you for your nice presentation. What is the laser pulse energy and laser pulse duration, length, laser pulse length you used?
What's the parameters?
What is the magnitude of laser pulse energy and the laser pulse length you employ for this purpose?
Okay. In our system, so we use different varieties of lasers, like UV lasers and visible lasers, IR lasers. So we can vary the wavelength, and 1064, like an ND-YAG laser, 1064, and 532 nanometers, and 352 and 256 nanometer, or we can using the dye laser to control the visible to, IR region, and also using the CO2 lasers. But mostly we using the nanosecond pulse laser systems. So 7 nanosecond pulse width, and depending on the power is about 10 millijoule to several hundred millijoules. So it really depends on the system, but we explained very well in our papers, so everyone can follow. Okay, that's all commercially available lasers. Yeah.
Sir, good morning, sir.
Yes.
So I'm Dr. Variyar from VIT Chennai. Sir, you told based on for the mixing material we use for the laser processing part.
Sorry, I cannot clearly hear.
Sir, you told based on for laser processing material using the mixing material based on 2D material.
Mixing?
Mixing supercapacitors material. So it's adapted for all supercapacitor material? The laser processing for energy, battery or supercapacitor materials?
Sorry, clearly
the same laser process is adaptive for all supercapacitor material, like charcoal, carbon and battery materials for synthesis.
I cannot clearly. Oh, okay, somebody. Yeah.
Come
yeah.
forward. Can you please
he
come
is asking
forward?
whether this technique can be applicable for all the materials, energy storage material like battery material or supercapacitor material. One example you mentioned Maxine, that is a good energy storage capacity. Can we apply for other material also this laser technique?
Oh yeah, sure. Yeah, I mean, we can use, as I shown before here, so we can use all different kinds of material, the metal, nanoparticles, and other things, and also we can apply to the some other, organic frameworks too, using the laser. And so metal organic framework that I mentioned before, very last moment, as ZIP, and other things applied for the supercapacitors and other things. But we tried it. So it depends, as I say, I mean, chemistry and experiments all depending on the situations and circumstances. And it works for some cases, and it works sometimes not. So you have to do the trial error things. You have to understand the mechanisms of formation of nanoparticles, and also, like for example, like mentioned the supercapacitor, and also photocatalysis. You need to control the band gap, of the metal, oxide materials, or by controlling the gap between these, HOMO and LUMOs, and other things. This is this. So it depends on the material itself, and depending on the systems you're working on, and others, environment you're working on. So if you have any questions, just directly ask emails or contact other contacts. So we'll explain in detail. Okay, thank you very much.
Good afternoon, sir. So, let me introduce first. I am Alex Babu. I am from Medical College, Alappuzha, working as assistant professor in pharmacy. So nowadays, this pharmaceutical field, this nanotechnology is emerging, and I thank you, sir, for this excellent presentation on this nanotechnology, and for your kind consideration with the collaboration with India. That is very good. And my discussion regarding that basic concepts, that is regarding that synthesis, there is 2 levels there, up to bottom and bottom to up. So which one is good, sir, regarding that synthesis? And one more question is that there is ablation techniques, sir. So when we are applying that ablation techniques, which type of ablation is very good for this nanosynthesis? And regarding that green synthesis also, the environmental safety concerns also. Thank you, sir.
Okay. Thank you very much for your excellent question. And the first question you ask is whether the pulse laser ablation in liquids or pulse laser irradiation in liquids, which is better or not. I mean, it depends on the system. So for the case of reduction, pulse laser irradiation, so which is without the lens, so you're using the light, and light as the like a reduction potential. So if the reduction potential is too high, so you cannot make the metal to reduce the nanoparticles in that case. So you cannot. So you have to change, as Professor asked, some maybe higher wavelength or higher power. So you need to apply it. But in general systems we're working on, and you cannot make all the metal ions to reduce. So depending on the reduction potential. And however, in this laser ablation system, as many people ask, it has really high power and high temperature, and high pressure. So it forms metal ions in plasma state, like metal cations, cations and anions are both present in the plasma flume, and then they make it, sometimes making in the nanoparticle, like a reduced, they recombinate from metal ions to the ions, the anions, to make the metal. So it's also depending on the system. So we use like a metal, depending on different kinds of metal. Okay, so that's the system. So we use differently. Sometimes we use irradiation to synthesize, reduce the metal ions to the metal. Sometimes we cannot. Then we do laser ablation to synthesize the metal nanoparticles. So that's the first question you asked. But second question, you the green chemistry something? I forgot, sorry.
So that was regarding that green synthesis, because environmental safety regarding that. Any additional points?
Oh, okay. For the environmental point of view, so as I mentioned, this is byproduct free. It's like we don't use the chemicals, we use only solvents and metal, light, and no reducing agents or surfactants. So we don't use it. So for the general cases, if you use other chemicals, it produces byproducts, and it's harmful to the environment and other things. It takes a long time to work up other things. But here we only use laser, light, and metal, and solvent. Solvent is used for the production of graphite carbon layers. So what I would say is environmental friendly is in the beauty of these pulse laser ablation. So we don't use any other chemicals. Is that okay?
Thank you, sir. Thank you.
Thank you.
We'll take the last question for this session. Okay. Thank you. We would be very honored to have collaborations with you, sir. I'm sure you will come up with other cost-effective nanomaterials. You did mention about copper-based nanoparticles which are cost-effective. The first few slides indicated the amount of money you have invested in the equipment for this laser synthesis. I hope in the field of medicine you will produce cost-effective nanoparticles as well. And for research and collaboration, maybe the medical colleges which are affiliated to our university can do the collaborations with you as well. Thank you so much, sir. Kamsamnida.
Oh, kamsamnida. Thank you. Thank you.
Thank you, sir. Thank you, ma'am. We now request our chairperson, Professor Dr. Deepti Shastri, ma'am, to felicitate our speaker for the day, Professor Dr. Myo-Young Choi, sir.
Thank you. Now we request Professor Dr. Myo-Young Choi, sir, to felicitate Professor Dr. Deepti Shastri, ma'am. Thank you, sir and ma'am.
Thank you, delegates. Now you can leave for a small tea break, which will be for 15 minutes, and assemble soon back for the parallel sessions. Thank you. We request all the delegates to assemble inside the auditorium soon. We'll be starting with the technical sessions shortly. I request all the delegates to assemble soon inside the auditorium. We'll be starting with the technical sessions soon. Check. All the delegates, for your kind attention, we'll be having All the delegates, it's for your kind attention, we'll be having two parallel sessions. One session will be happening here in the Annapurna Auditorium, and another session will be happening in Annapurna Lecture Hall 1, which is in second floor of the hospital building. So delegates who are interested to attend here, please remain here, and other delegates, please go and get settled in the Annapurna Lecture Hall 1. Check. Delegates, please take your seats soon. I take immense pleasure in calling the next speaker for the day, Professor Dr. Anangnon Somwong Tonaroj, Associate Dean, Department of Chemical Engineering, Faculty of Engineering, Chulalongkorn University, Thailand. The topic she'll be dealing today is balancing between proton conductivities and iodine crossover of separators for zinc polyiodide flow batteries. The session will be chaired by Professor Dr. Divya Krishnamurthy Ma'am, Department of Prosthodontics, Vinayaka Mission Sankaracharya Dental College, Salem. Over to you, ma'am. Good morning, one and all present here. Good morning, one and all present here. It is my pleasure and privilege to introduce the eminent speaker of the day, Professor Anangnon Somwong Tonaroj, the Associate Dean and Faculty of Engineering at Chung Kong University, Bangkok, Thailand. She obtained her doctoral degree in macromolecular science and engineering from the University of Michigan, Ann Arbor, USA. Her research focuses on improving the properties of polymer to obtain the desired properties of polymer for the application such as bioplastic packaging for extended shelf life of fresh produces and processed food, and adhesives for electronic industries and separators for zinc-based batteries. Professor Annie has published 60 articles in high-quality journals and has an H index of 20. Professor Annie has founded the Garden Fresh, a spin-off that offers biodegradable plastic bags that can extend the shelf life of fresh produce for up to 5 times that of the normal bags in November of 2018. Then, due to the lack of high quality masks for medical frontline workers, Professor Annie and her team researched, designed and produced the half-face respirator and then co-found the Cure Enterprise, a spin-off which was launched in March of 2021. Until now, more than 40,000 of these Cure Air Sure
reusable half-phase respirators have been distributed throughout the country. And today, we have the privilege to hear from her on balancing between proton conductivities and iodine crossover of separators for zinc polyiodide flow batteries. The floor is all yours, ma'am. Thank you.
Thank you very much. So, Wanakam. Good afternoon, everyone. So, it's my pleasure to be here. And I came from Chulalongkorn University. The university is in Bangkok, Thailand. So, we are in the center of Bangkok. If you have any chance, please visit us. So, hold on. Sorry. Somehow it's go very fast. Okay, so our university was founded in 1917, and right now we have 21 faculties and schools, and we have 23 colleges and research institutes, and we have around 8,000 faculty members. And this is how it looks in the night. So we have the sky train, just around here. Okay, here. And so you are welcome. Okay. This is the Faculty of Engineering. We have 12 departments, and we have around 300 faculty members. And we have, for undergrad students, around 1,200 students a year, and for the grad student is around 500 a year. So for today, I'd like to tell you about our work in the zinc-based batteries. So for me, I'm responsible for the separator for the zinc-based battery because my background is in polymer. For the zinc, today I'd like to talk about the zinc polyiodide flow batteries that have potential to use as the large-scale energy storage system. For the zinc polyiodide flow battery, you can see that we have the zinc and we have the polyiodide, and we need the separator to make it work. We chose to work with the zinc. It's because it's cheap, you know that, right? And it's abundant. We have a lot in the world. And also it has high chemical stability, high theoretical capabilities. And also you can see that when right now it's for the reserve in the world is a lot, right? And the price is less than 40 times compared to lithium. That is not enough. So we think that this is a potential. And for the polyiodide, because you can see that the solubility of the triiodide salt is quite high. So that's why we choose to work on this system. Here, so this is how it looks like. The flow battery, we have two pumps, and then we pump the anolyte and catholyte into the system. And we have the separator that just let only the zinc ion to go through, but the iodine ion cannot go back to that side. Okay, and this is how it looks like, our system in the lab, the small one, but we plan to scale up this year, so let's see. Okay, this is how the reaction look like. I have to go fast a little bit. So for the if we want to scale up the battery to make sure that we can work for in the big building or in the electricity facility to to compensate it, when there is a surge. If we use the zinc iodine flow battery, the good thing is that that we have a lot of zinc in the world, and it's not low toxicity, and also it have the high theoretical capability of the zinc. We have iodine ion a lot in the world, and high solubility of the iodine and iodide. So this one will be the future of the energy storage system. But the problem is the separator right now is we use the naphthalene in some literature that work on this system, and the problem with the with the Nafion is that it's very expensive and it have low ionic conductivity and also it's low ion selectivity. So you can see here the price of the separator for the battery is around 40%. And for the price of Nafion, it's around 1,000 to 4,000 US dollar for 1 meter square. So it's very expensive. So that's why we decided we want to develop the new separator for that. The problem with the low conductivity, so when there is a low conductivity for the separator, the problem is that it will have the high ohmic polarization. And then we will just get the low voltage efficiency. So we decided, another problem is that low ion selectivity. So when there is low ion selectivity, it means that the iodide ion can cross over and it will lose the capacity. So from that, we decided to develop the separator so the choice for the membrane separator, there are 2 types. You can see that one is the ion exchange membrane and the second thing is porous membrane. For the ion exchange membrane, they use the Donald exclusion. For the porous membrane, we use the side sieving effect. So for example, the ion exchange membrane is the Nafion. The way is that they just, this is the micrograph of the Nafion after the cycling in the sieve. And there is a problem with the low chemical stability. So in this work, in other works, they use the PES, the polyether sulfone, as the base polymer because it has high thermal stability, high mechanical property, flexibility is good, and it's cheap. But the problem is that the hydrophilicity is still not good, and also no ion exchangeable group. So we developed from that is that we mix the PES with the sulfonated PEEK, polyether ether ketone. So the good thing is that now we can modify the property of the membrane by, play with the morphology of the membrane by mixing it, and then change the condition by changing. Like this one, you can see that the micrograph show the finger-like structure. So it means that the ion can go through very fast. It's not good. So we have to change the concentration of the S-peak, and then the matrix will be bigger and then denser, and then we have the small part of the S-peak inside of the PES. And this is there are another work that they use some chemical to help it, but it's still not so good. So I will just go down here. Okay, so for our work, we decided we will use the mixture between S-peak and PES, and then we want to improve the ion selectivity by using the thin film of polyamide, the nylon, by using the interfacial polymerization to make the very dense thin film, to make sure that only the small ion can go through, but the iodide and iodine ion cannot go through because it's bigger. So we can modify the membrane by using the polymer here. So this is the polyamide that we chose. The monomer is the MPD and the TMC, and we use the interfacial polymerization. This means that both monomer is in different solvent, and then when two monomer just meet each other, they will start the polymerization immediately, and then we get the very thin film of the polyamide on the porous substrate from the S-peak and PES. So this is how we develop our membrane. Okay, so we have the porous substrate, and then we put the thin film polyamide, and this is how it looks like. Okay, we can, and after we obtain the separator, the matrix. This is the porous substrate. So the SP is the S peak with the PES, and X is the weight percent of the S peak. So we vary it from 0 to 60. And then we fix the polymer concentration at 35. And we found that you can see that when we increase the weight percent of S peak, the water contact angle decrease, so it means that it have more hydrophilicity, so it's good. And now we look at the appearance. We know that the one that doesn't have the S peak at all is not, even though the film look good, but the property is not good. But for the one that have too much of the S peak, the film is swollen, so it's not good. So we decided we get the 20 weight percent of S peak. And then for the micrograph of the cross section of the membrane, we don't want the finger-like structure, because the ion can go through very fast and it's not good, because we cannot select it at all. You know, the selectivity is bad. So we like the sponge-like structure. It looks like a sponge. It's good. Okay. So now here we vary the polymer concentration, and when polymer concentration is too low, so we have the, when we use the phase inversion technique, that one is like, have the finger-like structure and have the macro void. So the macro void is not good. Everything can go through. So we like this one, the one that have the optimal property, that is the one that have 35 concentration of the of polymer is 35. We obtain the sponge-like structure here. Okay. So after we got the optimal morphology, so we use the XTM to see the porosity of the membrane. And you can see that when we compare between the one that have increased the polymer concentration, it from finger-like structure to sponge-like structure, the porosity decreased from 51% total porosity to 8.9%. That is what we want. So we decided we will test the battery with this membrane. Okay, this is we characterized by the ATR, FTIR to make sure that we got the right porous membrane here. And then, okay, I will just go really fast here because we come quite late. And then after we make sure that we get the separator that between S peak and PES, blend it, and then we have the polyamide thin film on it, characterized by the FTIR. So now we check the property that we want for the battery, the triiodide ion permeability. We don't want the triiodide to go past the membrane. So we can see that the concentration of the iodide ion can, it can go pass through the membrane around 80 micromole. That is a lot. But when we have the thin film of the polyamide on the porous membrane, it go down to be around 11 micromole after 250 hours. So it means that it's much better now. And so now we check with we check with the proton conductivity, and we can see that for the proton conductivity, it from here, the one that we chose for the porous membrane, and then when we put the thin film of polyamide, the proton conductivity just decreased a little bit, but not much. It's still good. And when we compare with other membrane, our work is on the top four low. It's still good, right? Because the conductivity is still around 0.08 to around 0.08 to 0.04. But for other work, it's much lower here. And now we test the battery performance. You can see that the coulombic efficiency of the porous membrane, the battery that we use only porous membrane, it's go down pretty fast. it decays pretty fast. But for the one that we have the porous membrane with the thin film of polyamide, so the Coulombic efficiency is quite stable. After 100 cycles, it's still around 81%. And our voltage efficiency is 77%. Energy efficiency is 70%. So it's still quite good. And we check after the cycling, at 25, 50, 75, and 100 cycle. If we have only the porous membrane, you can see that the iodine can cross over it. But for the one that we have the thin film of polyamide, just, some part of the iodide ion can go through it. So, and this is we check before and after cycling. So we can see that the resistance in the system was developed after a while, because when iodide ion can pass through the separator, so it makes the system have more resistance and it works less. So and about the cost, we compare between our separator and the Nafion. So you can see that Coulombic efficiency, our Coulombic efficiency is a little bit lower than our system, but the voltage efficiency, our system is have a little bit better voltage efficiency than the Nafion. So, and also the price, you can see that the cost for our separator is only around 1/4 or 1/5 of the Nafion. So we think that we have potential to use this one for the large-scale energy storage system. So I'd like to conclude the talk is that so we successfully prepared the separator by using the phase inversion of the polymer blend between SP and PES. And then we use the thin film of the nylon, the polyamide, to make sure that there is a good ion selectivity. And then we test with the the battery system, the flow battery, and we have high Coulombic efficiency around 90% and high cycling stability. So finally, I'd like to thank the INEEBA organizer to invite me here. It's a pleasure to be here. And I'd like to thank PMUB, the Program Management Unit, for building capacity that support us for the research. And the Second Century Fund Chulalongkorn University that support my PhD student to work on this work. And this is my research group, my student, and all the collaborators from Korean and from other countries that join us in this year, February. So thank you very much.
Thank you so much, ma'am, for sharing your extensive research work, and the enthusiasm that you have for your research is just coming out of the pages when you speak about this. We open the floor for discussion. Any questions can be addressed to the speaker now. Yes. Can we have the mic, please?
Good afternoon, ma'am. Very informative presentation of technically. No, sorry. Okay. Thank you, ma'am. Based on for the flow batteries, what is the power density and energy density for compared to conventional batteries, ma'am? Asking for flow batteries, power density and energy density.
Okay, power density
and energy density compared to the conventional batteries.
Compare with lithium.
Lithium batteries.
Because for the flow battery, because we have the pump, so actually for the capacity we can increase it by just have more of the electrolyte of the system. So it's it's easy to scale up the capacity.
Yes, ma'am. Because I am asking for now is a hydrogen vehicle is coming, ma'am, based on next 10 years for the hydrogen based electric vehicle. Is flow batteries adaptable for electric vehicle applications?
Again, please.
Now it's coming for hydrogen electric vehicles. Hydrogen vehicles. Yes. Ma'am, now... yeah, okay.
Speak slowly, please.
Okay. So electric vehicles come based on, for the hydrogen-based electric vehicles coming. Hydrogen. Yeah.
Yes.
The flow batteries adaptable for electric vehicle applications? Flow batteries.
For battery. The application. Okay.
EV application. Electric vehicle application. Electric vehicle application.
Can these be used
Electric
for
vehicle. Okay, sorry. No, right now we think about not for mobility. We like to work on the stationary because it's like we have a pump. We have to have the the reservoir. So it's supposed to be stationary. Is supposed to be better option for the flow battery.
Okay. Thank you, ma'am.
Thank you.
Thank you so much for the question. We would like to end this session by presenting ma'am with appreciation certificate.
Thank you.
Thank you so much, ma'am. We now request Professor Dr. Divya Krishnamurthy, ma'am, to felicitate Professor Dr. Anagnath, ma'am. Thank you, ma'am. We now request Professor Dr. Anagnath, ma'am, to felicitate Professor Dr. Divya Krishnamurthy, ma'am. Thank you so much, ma'am. We now will move to the next technical session by Professor Dr. Manasvi Suthipan, Assistant Professor, Department of Chemical Technology, Faculty of Science, Chulalongkorn University, Thailand. The title will be Insights into Solvation and Dynamics of Aqueous Electrolytes for Zinc-Ion Batteries. This session will be chaired by Professor Dr. P. Gnanasekar Sir, Director, IQAC, Vinayaka Missions Research Foundation, deemed to be University, Salem. Over to you, sir.
Good afternoon. Sawadika. Annyeonghaseyo. I think I'm right. Okay. It's my pleasure to chair this session by Dr. Manasvi Suthipan from the University of Chulalongkorn, Thailand. Dr. Manasvi is a lecturer in Department of Chemical Technology at the Faculty of Science, the Chulalongkorn University, Bangkok. She holds a PhD in Chemical Engineering from University College London, UK. Her research lies at the intersection of physical chemistry and chemical engineering, a rare combination, with a primary focus on employing molecular simulation methods to tackle challenges within the chemical engineering field. One particular area that captivates her interest is battery electrolytes. I think today we have more topics on batteries, which is very relevant in this era. Through the use of molecular simulation techniques, Her aim is to explore and provide answers to crucial questions related to the manufacturing and design of materials and devices for efficient energy storage. We have with us Dr. Manasvi on the title Insights into the Solvation and Dynamics of Aqueous Electrolytes for Zinc-Ion Batteries. Over to you, Doctor.
Thank you for your introduction and very warm welcome. Let I start with my department, the Department of Chemical Technologies. Oh, I don't think the voice is not come with. It's okay, it's okay. I can skip this part. I can skip this part. It's okay, I can skip this part and go to my talk directly. So just want to introduce you about my department.
Given by Thailand's Council of Engineers. Higher education at Chemtech comprises Master of Chemical Technology, Master of Fuel Technology, and PhD in Chemical Technology. The master programs aim to produce skilled engineers with deeper understanding in chemical technology and fuel technology. Chemtech's doctoral program accommodates students who need to develop more intensive backgrounds in areas of interest and the use of advanced analytical techniques to solve their research problems. Chemtech has established 5 distinctive research areas. The first is environmental and safety that focuses on environmental-related problems, solving and improvement of safety performance. The second is electrochemical devices, which involve the development of materials and catalysts for clean and sustainable energy application. The third is fluidization technology, emphasizes design, operation, optimization, and control improvement of fluidization systems. The fourth is synthetic fuel, which involves modern technology for carbon sequestration and fuel synthesis from renewable sources. The last one is green polymer, focuses on improving rubber properties and developing advanced plastics for future materials. Chemtech envisions students as an important part that pushes its mission forward. The department provides students with both academics and social events to retain school spirit and traditions. Typical Chemtech students will find themselves work hard in the classroom and at the same time will be active outside among colleagues, fraternities, faculties, and technical staffs. For nearly 6 decades, it has been a deep pride to see students' success and chosen careers after graduation from Chemtech. Potential jobs include production, process development, design, or fundamental research in a wide range of industries such as petroleum and petrochemical
Thank you. We are looking for graduate student and postdoc for position. If you interested in chemical technology, yeah, we are welcome and can contact me via email. All right, let's move to my talk. Our presentations will comprise three main parts. First is aqueous electrolyte for zinc-ion batteries. In this part, I will focus on effects of concentration and anions. Second, I will move to ether-water hybrid electrolytes for zinc-ion battery. In this section, theta-ethylene glycol dimethyl ether or TEG-DME will be added in the aqueous-based electrolyte, and we will see the phenomena of zinc-ion batteries. And lastly, we will talk about new electrolyte formulations for safer lithium-ion battery. Ladies and gentlemen, when it comes to the world of energy storage, zinc-ion batteries stand out predominantly, and they do so some very compelling reasons. Two primary strengths: cost effectiveness and energy storage capacity. And for the benefits of metallic zincs are like undeniable, including high abundance, high theoretical capacity, and low redox potentials. Zinc-ion batteries stand out as a leading choice for grid-scale energy storage. For example, low-cost, alternative, safer system, and they are easy to process and also have high ionic conductivity. Zinc-ion batteries are complex assembly. As you can see here, the system of the zinc-ion battery is composed of zinc anodes, cathodes, separator, and electrolytes. My works focus on electrolytes in zinc-ion battery. Electrolytes facilitate the transport of zinc ion between the two electrodes, as you see from the figures. The interplay or the relationship between ion dynamics and electrolyte property, both physical and chemical properties, can shape the efficiency and the mechanism in zinc-ion battery. So, if we want to improve zinc-ion battery, like for last longer, fast charger, and can store more energy, we need to understand the relationship or the interplay between the ion dynamics and these characteristics. In aqueous electrolyte, the solutions occur as water molecules surrounded the zinc ion, as you can see from this slide. This solution structure can affect the mobility of zinc ions and the interaction with other species in the systems. Under certain conditions, these solvated structures can be dissolved and can form the water molecules surrounded the zinc ion can form the active water molecules. These active water molecules readily to be decomposed, or I write down here is like chemically active and reactive. So what we see here, like many side reactions. For example, gas formations, material building up like dendrite, and also some of byproducts, and also some of corrosions. Belonging to this side reaction, understanding the interactions is very important for enhancing water-based electrolyte. So the main goal of my work is try to illuminate the solution structures and dynamics property of zinc ions in aqueous electrolyte. So to understand such behavior, I perform molecular dynamic simulation via GROMAX software. The simulation performed under NPT and followed by NVT assemble. As you see here is like ambient conditions. The simulation time is 10 nanoseconds with the time step of 0.001 picosecond, like it's very short simulation time. The force field applied in my work is OPLSAA for zinc salts and SPCE for water. And the simulation occur in the box like this. We consider the effects of concentrations and ion types, including zinc sulfate, zinc triphase or zinc OTF, and zinc TFSI or zinc bis triphase. This zinc salt can be fully dissociated into zinc ion and anions. Alright, let's move to the results. To analyze the structure, we use the RDF or radial distribution functions and coordination number between the zinc ion and the oxygen atoms of water molecules across the radial distance. So on your right is the RDF, right? Left is the RDF, and your right is coordination number. What you see here as low concentration or the back line here, or black, blue, or green line, right? That zinc ion can bond with like almost 6 water molecules, forming the structure like this. For example, zinc with 6 water molecules in 1 molar of zinc sulfate, and these 6 water molecules ready to be like it can turn to be active water. When we increase the concentration, we saw fewer molecules of water molecules surrounded in the first solvation shell. This can reduce the solvent effects in the red line right here. Okay, and for the anion types, we also see the effects of the change of the first solvation shells. For example, zinc sulfate compared to zinc TFSI, you can see here zinc TFSI can reduce more the solvent effects compared to the zinc sulfate. We further calculate the association between the zinc ion and its anion. We can see that the compact structure of sulfate ions as well as TFSI anion here can form a closer ion pair compared to the TFSI. At low concentrations, the bulkier TFSI here, we obtain the solvent separated ion pair. That means you cannot see the association between the zinc ion and anion. So the larger anion here can decrease the ion association. So, however, at 2 molar concentration, only zinc ion and TFSI and ion can associate together, like here. So why this importance? It's gonna affect the dynamic property of zinc ions. All right. So here I calculate the cell diffusion coefficients of zinc ion and anion. What you can see here as the concentration increase, the diffusivity of both anion, both cation and anion decrease. When we compare between each system, we find that zinc ion exhibits less cell diffusivity, right? Or it can mobile slower than anion because it's more bulkier. Zinc cation surrounded by water molecules. Zinc ion in sulfate system show the lowest diffusivity as shown in the back line due to the strong association between the ion pair. So when zinc it's moved with an ion, right? So it can reduce the mobility of zinc ion, and we not prefer. Next is ionic conductivity from the diffusion coefficient of both cation and anion. We can use Nernst-Einstein relation to compute the ionic conductivity, and we find that the ionic conductivity is proportional to the diffusivity of both ions. And the key message that we obtain from this study, like an optimal concentration might work well with one type of anion but not another. Like for example, if you compare like zinc sulfate, the best concentration gonna be 0.5, while in the however for the zinc OTF system and TFSI system, the best concentration is about 1 molar. And another thing is a particular anion might perform best at specific concentration, as I stated before. So to get the best electrolyte performance, so we must carefully select the right combination about the concentration and the type of zinc salt. Okay, next is the ether-water hybrid electrolyte. Here we study the electrochemical stability of zinc electrode in different hybrid electrolytes, and we find that TEG-DME show the best, right? The best electrolyte compared to the base case. The base case is right here. And TEG-DME water mixed with water cyclized was like about 11 times longer than the base case. This means that it shows the superior properties compared to only the aqueous electrolyte. From the experiment result, we complement our finding by using molecular dynamic simulation to see the behavior and mechanism of TEG-DME in the system. And we find that for the base case here, zinc cation coordinate with 5 water molecules and 1 OTF and ion. When we use hybrid electrolyte, zinc ions can coordinate with like 2 water molecules and the 1 molecules of TEG-DME. As you can see here, with this solvation structure, we obtain lower molecules of active water. As such, we can reduce the effects of side reactions, right, that can be occur. This is just like explain the solvation structure that I said before. So you can see here the red line in the middle graph is a coordination number in different electrolytes. So when the amount of TEG-DME increase, you can reduce the interactions between zinc ion and water molecules. That means you can reduce the solvation effects. And finally, you can lower the water activity, and therefore you can reduce the undesirable reaction. For example, hydrogen evolution reactions. So this is just validate our simulation result by using FTIR and Raman. But it just tell you that there is showing the shape of the curve between bending vibration and OS stretching vibration of water molecules. So we conclude here that the TEG-DME hybrid electrolyte can weaken water-hydrogen bond in the system. Okay, so the key point here is TEG-DME can mitigate hydrogen evolution and curtail zinc corrosions. So both simulation and experiments can tell you like TEG-DME hybrids with water can help you to modify the hydrogen bonding in the electrolyte and zinc ion solvations. So, do I still have time, sir? Like, there maybe 5 minutes. So, last part is about new electrolyte formulations for safer lithium-ion battery. Here, I show like application of lithium battery in everyday life. You can see like in phones, laptops, EV cars. So wise to make lithium-ion battery better, like last longer, be safer, and hold more energies. Same as zinc-ion battery, lithium-ion also contain electrolyte, right? So the electrolyte play important role into key aspects. One is control the transport of lithium-ion between the two electrodes, and also influence the interfacial interactions between electrolyte and electrode. Most commercial lithium-ion battery use liquid electrolytes, and the types. Most commercial lithium-ion battery liquid electrolytes are non-aqueous and mainly contain of mixed carbonate-based solvent. And these mixed carbonate-based solvents can cause have low non-flammability. That means very low safety, right? And also can provide low ionic conductivity and therefore low lithium-ion transference number. So this affects low performance of lithium-ion battery. So in order to solve the problem of the safety, researchers try to add co-solvent into the system. So for example, they put some sulfur content like TMS, novel fluorinated or FD37 organic solvent, and also succinonitride or SN solvent in the electrolyte. And they find that this co-solvent can reduce the flash point and also like can develop lithium-ion batteries with high safety. So there is from the experiment, there is a gap in our understanding regarding to how this co-solvent interact with other molecules in the system, and how this co-solvent influence the overall behavior, like the solvation structure and dynamical properties. I found that recent advance in MD simulations can provide significant insight into electrolyte solvation and dynamic property, like I said before in the part of zinc-ion battery. So in this work, we want to expand our knowledge to study the effects of co-solvent in order to develop the new electrolyte formulations. So we investigate the effects of co-solvent contents and co-solvent types, including TMS, DMSO, FEC, and SN in the bulk electrolyte solution using molecular dynamic simulations. And this is the system that we consider. We use the most common lithium salt, lithium PF6 at concentration of 1 molar in mixed carbonate-based solvents, and we add some non-flammable co-solvent, including TMS, DMSO, FEC, and SN at different ratio. We use same method, and what we found that as the co-solvent increase, so co-solvent content increase in the system of TMS, FEC, and SN, the radial distribution of the peak changes significantly, as you can see here. But in the DMSO system, there is the change of RDF peak significantly. So the DMSO content strongly affects the interactions between anion pairs in the system. Okay. And next is the coordination number. As you can see here, as co-solvent content increase, the interaction between the carbonate-based solvent also decrease, right? In the system of TMS, FEC, and SN, lithium ion and anion form contact ion pair. That means they stay together. While in the DMSO system, they want to separate, like lithium in the center surrounded by solvents and anions. And you can see here PF6 anion not participate in the first solvation shells. All right, and we find that the diffusivity of ions for the system of TMS, FEC, and SN, when the content increase, the diffusivity of the lithium ion and PF6 and ion decrease. How interestingly, in the DMSO, when the content of the DMSO increase, the mobility of both lithium cation and PF6 anion increase. And from here, we can calculate the ionic conductivity as is proportional to the diffusion coefficients. So the ionic conductivity of the MSO system, as you see here, increase as the weight percent of the MSO increase. And next, we calculate the transference number, and we conclude that the best weight percent is about 25 here. Okay, and from the solvation structure, we can see that the MSO can replace all carbonate-based solvents like zinc, lithium ion associates strongly with the MSO. All right, so and in the DMSO here, it can reduce the interaction between ion pair. That means lithium ion can mobile in the electrolyte like faster than other because the size of the solvation shell is smaller. Okay. So finally here, I conclude that the solvation structure, dynamics, and also electrochemical property depend on co-solvent contents and types. We use molecular dynamics simulation to predict the best formulation is about 1 molar of lithium PF6 in mixed carbonate-based solvent, and with adding 25% of the MSO. Okay. Finally, I would like to thank the financial support from PMUB, Asahi Gas Foundation, and Fundamental Fund 2023. I also thank NECTEC and Thai SC for computational resource, and I would like to thank CU Energy Storage Research Team, and most importantly, INEEBA 2023 for having me here and sharing my work. All right, thank you for your attention.
Thank you, Dr. Manasvi. Usually we think Thailand is famous for tourism, but after going through these two presentations, Thailand is a happening place for research rather. And specifically, we have seen both the presentations, they have been dealing with batteries, and that too zinc ion batteries. See, the difference between the normal lithium ion and the zinc ion is the volume of storage. So zinc ion is used for huge storage rather than lithium ion, where it is used for smaller storage. So it is really wonderful to see that very good research is going on in this area. We'll have the floor open for just 2 questions.
Thank you for your wonderful lecture, madam. In your first work, you have studied the solvation effect with a zinc zinc sulfate triplet. You have tried and compared there. Why did you ever tried with other than zinc metal? You have tried with a zinc sulfate, zinc triplet like that. You have studied the solvation effect. Why not you have ever tried with calcium, magnesium, other metals?
Slowly, please.
In your first work, madam, you have studied the solvation.
First talk, right? Yeah. I studied the effects of concentrations and types of anions.
Anions you have tried. Did you change the cations like zinc with other metals? Comparison, did you ever tried?
Oh no, just only this. Just only this one. And what that? Oh, zinc. Oh, because it's cheap. Yeah, and abundant in the world. That's why we select.
But you have
zinc
tried
metal.
with theoretically only. You can try now.
We can try with sodium and other metals too.
My question is, did you ever try the results, obtained results are same like zinc sulfate?
No, just this. Yeah.
Okay. My next question is, any of your obtained theoretical results experimentally proved or not till now? Your theoretical results, any of the theoretical results will proved by experimental also?
Yeah, we do have some, like we track hydrogen gas, but I haven't shown here.
Okay.
Yeah, and the result is in agreement with my simulations. Yeah.
Your obtained the theoretical results will give same results like experimentally also?
Yeah.
Okay,
thank you. Sorry, we can discuss later. I'm not familiar with an Indian accent, sorry.
Madam, good afternoon, madam.
But I try.
Thank you, madam, for the very good presentation. That was very nice presentation. And very pleasing experience we got. And here my question is regarding that nickel lithium-ion battery. Regarding that lithium-ion battery, it is an alkali, lithium, sodium, potassium, alkali metals. And when we use this zinc, this is a heavy metal, whether any problems regarding that metal poisoning? And one more question, that is I am teaching their pharmacy students, and some are interested in this biosensor technologies. So any courses are there in Thailand for fund supported for these students regarding this biosensor? So, okay.
Can you in Thailand? Biosensor.
Biosensor.
Oh, I have no idea about this. Sorry, sir.
Okay.
Yeah.
So she is from chemical technology, so I don't think she is
Yeah,
the right
about
person to answer that.
technology, it's like very far from my field.
Okay,
Yeah.
thank you.
Sorry about that. Thank you very much.
Thank you, Kaputka, and thank you all for this wonderful session.
Thank you so much, ma'am. Thank you so much, sir. We now request Professor Dr. P. Gnanasekar, sir, to felicitate Professor Dr. Manasvi, ma'am. Thank you. We now request Professor Dr. Manasvi, ma'am, to felicitate Professor Dr. P. Gnanasekar, sir. Thank you so much, sir and ma'am.
We are now moving to the next technical session. The session will be carried over by Dr. Tirthagiri sir, Senior Scientist, Brainpool Fellow, Core Facility Center for Photochemistry and Nanomaterials, Research Institute of Natural Science, Gyeongsang National University, Republic of Korea. The title will be metal alloys as efficient catalyst for hydrazine-coupled energy-saving hydrogen production. This session will be chaired by Professor Dr. B.S. Venkateshwarlu, Principal, Vinayaka Missions College of Pharmacy, Salem. Over to you, sir.
Thank you. It is my pleasure to be in this session as a chairman. Dr. Tirthagiri Jayaraman is currently working as research professor, brain pool fellow in the Department of Chemistry, Gyeongsang National University, South Korea. His current research is focused on the development of electrocatalysts for the production of energy-saving fuel and value-added chemicals. Professional involvement of Dr. Tirthagiri as editorial board in Bioengineered and Science of Advanced Materials journals, associate editor in Chemical Paper Journal. He has published 146 referred papers in high-impact international journals, edited one book for Elsevier, 11 book chapters and 3 patents to his credit, and delivered several invited keynote plenary lectures at international conferences and academic institutions. Now the dais and the session is all yours, sir. Please take care.
Thank you. Thank you, Professor. Thank you for your nice introduction about me. So good afternoon all. So I can understand that we are running in the lunch time. I don't know why I always goes in the edge of, timing. So I try to complete my talk within 15 minutes if possible. So myself, Dr. Tirthagiri Jayaraman, currently working as a research professor in Professor Myung Choi Research Group, Gyeongsang National University, South Korea. I will share some of my research experience on the title, Metal Alloys as Efficient Catalyst for Hydrogen Coupled Energy Saving Hydrogen Production. So yeah, so this is the Gyeongsang National University overview. So so this is the Gyeongsang National University overview, and our lab is located in the 7th floor of BNET building. So these are our lab outlook overview. So I will go in first. Our university, Gyeongsang National University, is located in the Jinju, south part of South Korea. So every year we celebrate in the month of October Jinju Lantern Festival, which is one of the famous festival in Jinju. And here I have shown some of the Korean traditional food. So I am sure that once you visit, you can enjoy the Korean food and other cultures. So as Professor mentioned, our research group is mainly focused on the development of various functional material using pulse laser technique, which are categorized into pulse laser ablation and irradiation. So once we synthesize these various material, we applied for the energy, environment and sensor application. So once you want to know more fundamentals about pulse laser technique, you can refer our recent research articles, which is published in Light Science and Application, one of the top journal in Nature publication. These attract the most cited paper in this journal particularly. So let's go to our topic, electrocatalytic hydrogen production via water splitting. So hydrogen can be used as a energy and fuel production and industry and feedstock for the various chemical production, I mean value added products such as ammonia. So there are various technique which is available for the production of hydrogen, but still this electrochemical water splitting considered as a green process, green chemistry process. So we know water which consists of H2 and O2. When we split electrochemically, H2 produced at the cathode part and O2 produced at the anode part. So I have categorized the op-cell reactions. So one electrolyzer is a full cell device which contains anode and cathode reaction. So op-cell reaction, which is hydrogen evolution reaction, which takes place the theoretical potential at 0 volt in reversible hydrogen electrode, and oxygen evolution takes place at 1.23 volt. So for better understanding, I have summarized the op-cell reactions, HER and OER, and the overall water splitting. So water, which is a liquid which is split into H2 gas and O2 gas. So both oxygen and hydrogen is a value added product, and hydrogen mostly used in COVID time. We were lacking in the hydrogen cylinder, I mean even oxygen. So the performance, main performance of the water electrolysis mainly depends on the catalyst which we used at the cathode and the anode part. So designing of material and cathode material or anode material is highly crucial. When we go for when we go for the search for a new material, we should focus these parameters to improve the activity of electrocatalytic material towards oxidation or reduction, and the stability. Any electrochemical device which mainly depends on the stability, we have to focus this parameter, and selectivity. So here I mentioned water electrolyzer which contains two op-cell reaction, HER and OER. A person he can choose to work in either HER or OER side also, only one reaction. So one material it cannot possess both active in HER and OER. So we need to select the material criteria for whether I should be focused on the anodic reaction or cathodic reactions. So selectivity is the main criteria here, and to reduce the overall operational cost, and investment cost, and increase the lifetime, which is almost similar to the stability, and avoid the pollution. When we go for any research, we need to go for like a green chemistry process. As I mentioned, this electrochemical water splitting is a green chemical process. So we have chosen this path to go, carry out our research. So pulse laser technique, in the first talk, professor has mentioned clearly and gave the brief introduction or fundamentals about the pulse laser technique. Still I want to give some information. This pulse laser technique, in our lab even still there is another technique of pulse laser deposition which they do for energy storage devices, but we go with the liquid process, pulse laser ablation in liquid, pulse laser irradiation in liquid process. The main differences, what are the difference between this ablation and irradiation means? So this ablation is a top down process, which means the bulk material to fragments. Similarly, in pulse laser irradiation is a bottom up approach method. This is a metal ion into nanostructure, various nanomaterials we can synthesize. And the prime differences is in pulse laser ablation we can use a focused lens to focus a target material to produce a metal ion. These metal ion will interact with various fragments from a decomposed solvent which we use as a liquid. So it produces a material. And irradiation we mostly use it for the unfocused lens, the colloidal solution. So from the colloidal solution we can synthesize a nanomaterial. So I can explain the mechanism in the forthcoming slides. So overall this process, we have so many synthetic routes like conventional technique, hydrothermal, solvothermal or co-precipitation, various techniques are available. What are the advantages? Overall this pulse laser process is a less complex, simple and clean, reproducible, eco-friendly and byproduct free. So I don't want to go in depth each step, so explanation due to the time limit. So these techniques, so when I mention it should be a pollution free technique. When I talk about the green chemistry process is a hydrogen evolution from the water splitting. Similarly the technique which we use to produce the nanomaterial which also a green chemistry process, because we don't need to use external surfactant or capping agent to control the size and morphology. Most of the research at present mainly depends on the tuning in the surface or size, because the electrochemistry is a surface reaction. Most of the HER or OER is a surface reaction. It is surface between the electrode and the electrolyte. So we need to tune the surface morphology. When we tune the surface morphology, we can attain the high number of active center and number of active sites, which we can also estimate using a electrochemical process. So I don't want to go in more depth in how to calculate and how to extract the active sites, but still I can show how we can identify the phase transition, which is the active center, like this in the next slides. So when what are the disadvantages when we use this surfactant in a conventional technique? For example, hydrothermal or solvothermal, they are using a surfactant to control the morphology. What happen if we use surfactant means it block, the nanoparticle, it cover the nanoparticle, this surfactant, which enter the active sites, number of active sites. So these active sites are responsible for the enhancement of electrochemical application. For example, electrochemistry is a surface between the electrode and the electrolyte. So it can block the number of active sites and which reduce the activity. So here in this case of pulse laser technique, we have this kind of issues, and also we don't require the additional reducing agent to reduce the or produce the material. For example, if I want to produce a nanoparticle using a metal salt, I require highly toxic and chemical reagent. For example, sodium borohydride required. One of the example is a sodium borohydride is a strong reducing agent which reduce metal ions into metal nanoparticle. But in case of pulse laser technique, we not required any external reducing agents. So how it work, how it form, how it produce the material, which I can explain in the same slides. So there is no byproducts. So whatever we decide product, there is no side product or secondary reaction which takes place in this technique, and the experimental setup is simple and minimal, offering a low cost method. So in this work we have integrated. So not only we are focusing on the single technique, we are trying to adopt the integrated, fabricate the techniques to produce highly active material. So for example, in this work we have integrated pulse laser irradiation and sonochemical process to produce nickel palladium alloys. So in the first step, what we taken is a pulse laser ablation of nickel target, nickel plate. So when we ablate nickel plate, it produces a nickel ion, and finally it react with a decomposed solvent, hydrogen radical. It produces a nickel colloidal solution. So how it form? For example, when we ablate the laser, when we pass the laser, the metal, it produces metal ions. Simultaneously, the solvent which we used, so that is why we mention pulse laser ablation in liquid, pulse laser irradiation in liquid process. The liquid stands for the solvent. So these solvents also decomposed. While passing a laser, the solvent decompose and produce the fragments. For example, when we use the water, it produces hydrogen and hydroxyl radical. So these hydrogen radical is means for the strong reducing agent to reduce the metal ions which produced from the metal target. So and some in case of methanol or other organic solvent, when we irradiate it, it produces even hydrogen radical or methane radical, still hydroxyl radical. So these methane radical further decompose into produce the carbon fragment, various carbon fragments. So these carbon fragments can also interact with metal ions produced. It can produce a desired product. For example, metal carbide or nitrate based on this. So solvent. Here the laser parameters, not only laser parameters such as wavelength and the distance and the energy, the first question actually asked by Professor, not only the laser parameter, the solvent also is play an important role, major role. That's why we mention in the technique itself, pulse laser ablation, irradiation in liquid process. So here in this case, it get reduced and nickel colloidal solution produced. Then we added a palladium salt. Then we have further gone for a irradiation step. These all under the ultrasonic irradiation process. So what happened when we integrated means we know the ultrasonic process is a sound wave process which can also produce radicals, hydrogen radicals by the sound waves. So when we have excess of hydrogen radical, that means reducing agent, the reaction yield will be higher. So this is the advantage. Reaction rate is very faster and yield will be higher. Not only a yield, but also the morphology we can control. I have compared the pulseless irradiation where non-uniformed surface morphology, but when we compared with the ultrasonic process, so we could get a uniformly distributed particles. So in our research then we trying to focus, either in the sonochemical process or just stirring based on the reaction and particles. So we have fixed this condition using this experiment. So this work was published in 2021 Chemical Engineering Journal, and Professor Ashok Kumar Muthupaneni is the editor-in-chief of ultrasonic sonochemistry. He is a well collaborator with the professor. Okay, another work we have prepared AUPT alloys for the hydrogen oxidation reaction. Some of the works morning professor has explained very clearly, so I want to give some information, additional information about this. So we have prepared using a AU and PT salt, then we have irradiated in methanol solvent. Within 10 minutes we have produced this material. So in case of, if I want to go for a conventional technique like hydrothermal or solvothermal, is a time consuming process. Even in the next slides I can show the advantage, whether we can extend our technique to the other material or not, I can explain you. So in the second stage I have added a carbon black. Why? What is the advantage when we mix with the carbon black under the ultrasonic process means it's well dispersion of AUPT alloy particle. It leads to the well dispersion also conducting material. So we know the carbon black or any carbon material is a good conducting material, good supporting material, not only in the catalysis but also in the medicinal field. So once we synthesize this alloy material, we have gone for a water splitting, also hydrogen splitting. So water splitting, as I mentioned, it is a two opposite reaction, which is a HER and OER. Hydrogen splitting is a HER and hydrogen oxidation reaction. So in the conventional water splitting, I have replaced the kinetically less OER by a hydrogen oxidation reaction. So what happened when I replace this hydrogen oxidation is the overall energy input which dramatically decreased. For example, you can see here the overall water splitting, which is a 1.7 volt energy I need to provide to reaction occur. Whereas when I replace the OER is a 1.23 theoretical potential, but in hydrogen oxidation is a minus 0.33 volt. So when I add almost at the 10 milliampere current, I could save 1.5 volt I could save. So this is what I can say, this is a energy saving process. So we have gone for a optional reaction testing also before going for the electrolyzer fabrication. So in the HER optional reaction, the best performance material is when PT is a high percentage. For example, AU1 and PT 8%. This shows the highest activity. So we know the PT is a platinum, which is the highly active in most of the electrochemical application. This is also similar to the hydrogen oxidation reaction, but in case of OER activity, it hinder. So when we take highest PT sample, it limits. Actually, the result is not shown. And instead of this, AU4 and PT1 is the good active for the OER. This is what here I mentioned. The selectivity is really important to choose any reactions. So what happened? Why this conventional, PT is less active in case of OER means, when we do the electrochemical reaction, it is, as I mentioned, it is a surface reaction. So surface get oxidized and produce a PTO. PTO is a active center, active sites. If I take any material, that material itself won't act as a active center. It can go for a phase transition. Phase transition means on the surface it can produce various active center. This active center, it possesses a number of active sites. So when there is a more surface area, electrochemical surface area, the active sites, number of active sites will be higher and the activity will be higher. So in case of PT, it converted into PTO. So this PTO is less active for the OER reaction. So this is what the reason, and here we have shown the real images of hydrogen splitting and hydrogen, water splitting. So similarly, we have gone for other work, other alloys, copper PD and copal PD. These works we published in this year. The both work is published in Chemical Engineering and Journal of Materials Science and Technology. So I don't want to go in detail due to the time limit. Okay. So far we have seen a nanomaterial, alloy particles. We have also extended non-oxide material, that means carbide material. So what are the non-oxide material, which carbide, sulfide, nitride? Yeah, we can also synthesize using a pulse laser technique. Here in this work we have synthesized a series of transition metal carbide, copal carbide, iron, titanium, molybdenum carbide by the ablation of the corresponding metal plates. So what happens if I ablate the metal plate, the metal ions produce, then the solvent which we take in here, acetone. Acetone is which contains a carbon, it can split, during the ablation, laser ablation, the solvent decompose and produce a carbon fragments. So these carbon fragments interact with the metal ion to produce a corresponding carbide. So the advantage of this technique is, we know this metal carbide usually synthesizes the high temperature programmed reaction. For example, solid gas reactions. So solid we can take the precursor material, and gas is for example methane gas. Usually they take a methane gas. When we give a high temperature above 700 degrees Celsius, this methane gas decomposes and produce a carbon. Then it will react with the precursor and produce a metal carbide, and one is a high temperature reaction and also time consuming process. For example, we need to carry out in a inert atmosphere. Before starting a reaction, we need to pass either inert gases, argon or nitrogen, for 1 or 2 hours to remove inside, furnace oxygens. Then we need to carry out the reaction slowly. Heat ramping also we need to control. These kind of things we can avoid. The overall reaction is within 20 minutes we could produce a pure single material of this metal carbides. So here I have shown the selectivity. Again, the selectivity is the matter. In case of HER, molybdenum carbide possesses the highest activity. The reason is it is a more D vacancies. So when there is a more D vacancy, it is strong hydrogen affinity. So similarly in OER case, it has a copal carbide. The reason is copal is a less vacancy, and less D vacancy, and also hydrogen affinity is higher, larger. So we need to, I mentioned we need to study the phase transition, what happened during the reaction. That is what our prime interest. For example, I have shown here one of the in situ Raman, electrochemical Raman technique. During electrochemical process, copal carbide, it converted into cobalt oxyhydroxide, which is the active center. Still, when, for example, when we continue the prolonged reaction of electrochemical reaction, it converted into surface electro-oxidation of cobalt oxide. So here the active center is a cobalt oxyhydroxide, not the cobalt carbide. But I have taken the electrode as a cobalt carbide. Okay, so this has to be analyzed. So this work still we fabricated overall water splitting. And we have also extended our research for the fabrication of MOF material. MOF material usually synthesized using a solvothermal technique for a long term, time consuming process. So here we prepared nickel, cobalt and copper BTC in 10 minutes using a pulse laser ablation technique in DMFF solvent. So the beauty of this technique is, as I mentioned, we not required any surfactant or capping agent to control the surface texture. We can see here octahedral structure, copper formed in a octahedral structure and copal formed in a hexagonal structure and nickel form a seed-like structure. We have applied for the overall water splitting. In the all the process, cobalt possesses the highest activity due to the various oxidation state. Cobalt has the +2 and +3 oxidation state. So, and the surface area. So I mentioned when there is a more surface area, active site, number of active site will be higher. When there is a more number of active site, it leads to the highest electrochemical activity. So we have gone for a Maxine. Usually this Maxine work, we have in the pure Maxine we prepared a chemical etching process, and we added a PT salt. Then we have irradiated. What we observe is the platinum should deposit on the Maxine. But interestingly, we could observe the reshaping. We obtained the core cell. core cell structure. This is the beauty of our research here. So PT was decorated on the surface. The core, cell is a TIC is a cell and core is a TiO2. So TiO2 is a semiconductor property. So we have gone for the electrochemical and photoelectrochemical hydrogen production reactions. So this work published in this year in ACS Nano and featured as a cover image. So I would like to conclude my talk. I want to acknowledge the professor and director, Professor Myung-Young Choi, and other colleague members, for their support. And their dedicated work. So I want to mention here, in the last presenter, they were asking about the opportunity, even biomedical application. Even in the first talk also, someone was asking about the opportunity in their lab. So I want to show here in our lab, you could see here some PhD courses. There are many Indians, especially the Tamil person. Top two want to, first person is Kazakhstan, and the second is a Korean who is presenting here. And S.R. Akash Prabhu is from Chennai, and Saganta is from Kazakhstan, and Jayapal Anbarsan is from Dharmapuri. Actually, I am myself also from Dharmapuri, and Kasi Viswanathan is like Tirunelveli, Ramar is like Erode. And here in case of postdoc, you can see the Raja Armugam Sendil, he is from Tirukkoilur Viluppuram, and Veluchami is from Coimbatore. So what I can mention is, in our lab there are more scope. You can apply for the PhD, postdoc, even master. There are scholarship like GKS, Global Korean Scholarship, that is for the studying master and PhD. Even recently they offered for the postdoc also. Otherwise we can enter in a brainful fellowship. It is a reputed fellowship. So I entered with the brainful fellowship, government fellowship. You can apply for the fellowship to the government of Korea. So these brainful fellow, they offer a huge, fellowship. It is a, in the world it is a highest salary which we can get, like including house, like 6,000 USD as a starting, and up to 10,000 USD per month you can get it. You can apply it, and if a professor has a strong background, he can recommend also. So and apart from this, professor has a own funding. I think in his presentation he has showed a lot of funding. He is even the program manager for the national NRF, National Research Foundation. Even in the recently India government also, they are trying to merge all the CSIR, DST and BRNS in as a National Research Foundation of India. They want to come into merge and India single funding source. This was the BJP government as trying to make. So likewise, we have also National Research Foundation of Korea, which is the major funding. Professor was the program coordinator. He was the one of the director for selection of projects. So even there is a one secret that I also running one project on my name. It's all because of him. Even like Sendil also running one project on their name. Most of the research professors, we can apply our own funding. Even in my funding, you can apply. You can join. I can take one student in my funding. I can offer a salary for the master or PhD. You can go through and you can refer our website, Professor Myung-Young Choi. Even if you type in a Google, you can get it more detail. And this is our website. There we can post. You can see most of our research work, also the activities. Life at our lab. So you can look at there, and you can email either professor directly or myself. So most probably we can consider. So we are encouraging. So sometimes we used to talk with the professor. India is a huge country. Whereas, the last previous person, one person, past people is from Bangalore, Srianga. He completed his PhD and now he is in Canada. While we are chit-chatting, we were talking, oh, where are you from? Tamil Nadu. You speak Tamil. So, recently some visitors also. For example, from Bangalore University, even my professor, Tiruvallur University, they were visited last year. Even the group of Thailand people have visited our lab. So, professor is funding for a short-time visit also. Those who are working as a permanent position here, they can come for a short-time visit like 10 days or 2 months. Professor can offer your funding. He can bear all your expenses, living costs and also airfare. these options are also available. Even the students exchange program is available in our core facility center. Exchange program is available, like even our students are going US, for example, ESL went to Professor Kamat group in USA. Even most of the people like Arumin visited, even myself has visited Chulalongkorn University this year in the month of February. So last month, like Professor Aruna Kumari who also came here, she was visited for 2 months. So likewise, you can visit the research scholar or students, those who are really interested, you can visit for a short time visit. And the beauty is, what is the difference between the research in India and the, our lab is, I can give clear advantages. For example, professor has mentioned so many instruments, almost 30 major instruments. For example, it's one man, one-handed person, one lab. So after my PhD, I joined as a research scientist in Satyabama University. So when I applied and I went to sabbatical leave for like a short time visit only to South Korea. But I thought initially they gave 1 year, then I extended 1 more year sabbatical leave. Then after 3 years, then I resigned my position from Satyabama University. But still they don't want to give a resignation letter, experience certificate, but still I ignored. So I emailed to Vice Chancellor, I want to continue my position there only. So I like to continue, settle in South Korea with professor help. What is the advantage means, when I was doing a PhD here, if I want to take any sample, for example ACM, I need to send sample the Pacific Institute. For example, we know the IIT SAIP which has some specific instrument, but not all instrument. Even if you take any ACM or TEM, one private institution, they have like Satyabama, if you take ACM they have, but they charging a huge fund for one sample. And other, not only money, other thing is we don't know what happening. Once we send a sample, the person who is really taking our sample or other sample, that we don't know. And what I am expecting is mostly we are talking about the morphology oriented research. They not focus about our expected result. We give sample, they may give different results which may not be our expected one, but we have no option. We cannot go for a second shot. I cannot pay in second time, and also we don't have time. So like this, so my research is limited. But when I go and see there, every instrument, for example XPS, I don't know how many XPS available, maybe 3 or 4 in Tamil Nadu, maybe 3, 2, IIT having one XPS, and SAST, I don't know, maybe 2 or 3 may be available in Tamil Nadu. The XPS and ACM, XRD, and 2 electrochemical octation and the pulse laser lab. You can see that we have a 7 lab and with different techniques, pulse laser ablation, irradiation. So all the techniques which is GC-MOS and HPLC, TGA, DTA, every technique is by one man hand. So when I see my students, if I ask a research, give me a result, means he synthesize, then immediately he will check it in just a few steps back, he will check it and he will come with the results. So he is practicing by himself. All students, there is no technician, but there is some technician in a core facility, but we not. They also student. All students, including master, they are doing by themselves. So when we do by ourselves, practice our hands-on experience, that gives more knowledge about the research. So whether I am doing a right or wrong. So, and also practically we have like 30 group members. It looks like a mini company. Some of we will used to talk, gossip among our Tamil friends or Korean friends. They used to say, professor is running a company like this, mini company. Because 30 people including secretaries and everything, we feel like a company. So we have a practice, presentation every Monday. We have a lab seminar, like 3 research scholars, 3 students has to present, and we discuss and we can produce a good results. So I think I don't want to extend more time already. Thank you. If you have any questions, you can come, and you can, open to come apply our lab. So I can also strongly recommend your candidature to professor. So you have more scope. I am sure about it.
Okay, Jayaraman.
Thank you, Professor.
Very good session and a long session. So, South Korea is a clean city, I hope that, because of your efficient users of the energy efficient users, because the metal alloys are the major of the what need of the hour actually. The end use of any alloys is determines the selection of the metals, first of all. Because as a pharmacy graduate, I can say that is nowadays also this metallopharmaceuticals in the preparation of medicines also we are playing a vital role, because these metal alloys are placing in the formulations to release in the prolonged release this one, and in the preparation of titanium dioxide, the oral surgery also we are using this metal alloys. So what it is an eye-opener to the society, and your PLA and PLIs, that technology, I think it is a new technology what we are, I think it is implementing in your country, maybe. So it may eye-opener to the audience also. Now the session is open for the delegates to have clarify your doubts.
Yeah, thank you, Professor. Actually, I was only in the electrochemical field, but we have since three groups, three team of groups. They are working in a sensor as well as catalysis field, photocatalysis field also. But we major work, 80% of work mainly focus on the production of hydrogen fuel. So actually we have a plan to tie up with the Samsung company. You know the Samsung, which most of the LG and Samsung product available in our each home, at least one product. So we have a tie up with the Samsung company. We are going to the real application of hydrogen fuel car. So that is what we are progressing. Yeah, and also biomedical application. Some of recently we have sent, like a professor mentioned, TiO2. We have synthesized a black TiO2 that we give it for a cancer application.
And one division is also there for biosensors also.
Yeah, biosensor. Yeah.
Okay, good. Any questions from the audience? Okay. It is a long session already. Thank you.
Sorry, I thought to finish in 15 minutes. It went long. Sorry. Yeah. Thank you.
Thank you, sir. We now request Professor Dr. B.S. Venkateshwarlu, sir, to felicitate Dr. J. Teethagiri, sir. Thank you, sir. We now request Professor Dr. J. Teethagiri, sir, to felicitate Professor Dr. B.S. Venkateshwarlu, sir. Thank you, sir. Thank you so much, sir.
We'll have a lunch break for 30 minutes. Participants, please assemble back around 2:45 p.m. Thank you.